Consider a single grain of sand held between your fingers. Now imagine setting it down beside a beach ball. The difference in size is striking, but it is still something you can picture. You can hold both objects in your mind at once. What scientists have discovered about the largest structures in the observable universe is that this kind of intuitive comparison eventually breaks down completely. Not because the math becomes difficult, but because human perception has a hard ceiling, and the universe surpasses it by factors that defy everyday reasoning. Let us start close to home, with something concrete, and work outward from there. Jupiter is the largest planet in our solar system. It is a gas giant with a diameter of roughly 140,000 kilometers. And if you could hollow it out, you could fit 1,321 Earths inside its volume. That number already sounds large, but the more useful way to appreciate Jupiter's size is through what it does to the rest of the solar system. Because of its enormous gravitational influence, Jupiter acts as something like a shield for the inner planets. Its gravity deflects comets and asteroids that would otherwise travel on trajectories intersecting Earth's path. Scientists estimate that without Jupiter's presence, Earth would be struck by large impactors far more frequently than it has been over the past 4 billion years. The relatively stable impact rate we have experienced may be one of the reasons complex life had enough uninterrupted time to develop. In addition, Jupiter's gravitational pull helps maintain the near-circular shape of Earth's orbit. A more elliptical orbit would produce extreme seasonal temperature swings, making long-term climate stability much harder to sustain. So Jupiter is not just the biggest planet in the neighborhood. It is an active participant in whether the neighborhood remains livable. But Jupiter is not the largest planet scientists have found anywhere. For that, we travel 470 light-years from Earth to a gas giant called Roxas 42b. This object has a diameter roughly 3 times that of Jupiter. At our scale, where Earth is represented by a ball 12 centimeters wide, Jupiter would be about 1 1/3 meters across. Roxas 42b would be as wide as a large elephant or a modest single-story house. What makes Roxas 42b especially interesting is that it may not have formed the way most planets do. Standard planetary formation is a slow, cumulative process. Dust grains collide and stick together. Those clumps attract more material. Over millions of years, the accumulating mass eventually becomes large enough to pull in gas from the surrounding disk. That is how gas giants like Jupiter are thought to have assembled. ROX's 42b appears to have skipped that entire process. Its mass is roughly 9 times that of Jupiter, which puts it in a peculiar middle zone. It is too light to ignite nuclear fusion and become a star, but it is also far too massive to have built itself up grain by grain from a protoplanetary disk. Scientists think it may have formed through direct gravitational collapse, the same mechanism that creates stars, except there simply was not enough raw material available to push it over the threshold into actual stellar ignition. The result is sometimes called a sub-brown dwarf. It is a failed star, and because it never ignited, the heat it radiates now is largely residual energy from the gravitational collapse that created it. If you could somehow descend through its turbulent upper atmosphere, you would find a deep interior still glowing at temperatures high enough to produce a cherry red light. This object is slowly cooling, and it will continue to cool for billions of years into a dark, dense remnant. Before we move beyond planets entirely, there is one other case worth noting. The largest rocky planet scientists have identified is called TOI 849b. If Earth were 12 centimeters wide, TOI 849b would be roughly 40 centimeters across. Rocky planets do not grow much larger than about 4 times Earth's diameter, and the reason is physical. Once a rocky body reaches a certain size, it begins accumulating enough hydrogen and helium gas from its surrounding environment to transform into a gas giant. TOI 849b appears to be an exception because it is thought to be a planetary remnant, specifically the exposed core of what was once a full gas giant that had its outer atmosphere stripped away, probably by the intense radiation of its nearby star. What we are looking at is a fossil of a planet's interior. The point is that rocky planets simply cannot grow into the largest objects in the universe. For that, we have to look at what comes next. Stars. Our sun has a diameter of approximately 1.4 million kilometers. In the comparison where Earth is 12 centimeters across, the sun would be about 13 meters wide. It contains 99.86% of all the mass in the solar system. Everything else, every planet, moon, asteroid, and comet combined, accounts for the remaining 0.14%. The sun's scale of energy output is correspondingly enormous. Every second, it converts roughly 4 million metric tons of its own mass into energy through nuclear fusion, releasing that energy primarily as light and heat. The total power output is approximately 380 septillion watts. Over the course of a year, it loses a mass comparable to several hundred billion large passenger aircraft. Despite that, the Sun has burned for about 4.6 billion years and has enough hydrogen fuel remaining for roughly another 5 billion. The Sun is also extraordinarily loud, in a physical sense. Deep within its interior, the convection of superheated plasma generates pressure waves, which are technically sound waves that ripple across its surface. If space were not a vacuum, if sound could somehow travel the 150 million kilometers between the Sun and Earth, the noise would be comparable to a lawnmower heard at close range, even at that enormous distance. When a major coronal mass ejection occurs, the equivalent of hundreds of nuclear weapons detonating simultaneously, that sound pulse would be orders of magnitude more intense. But the Sun is, by stellar standards, a medium-sized star. It is classified as a yellow dwarf, and while that label is misleading in everyday terms since the Sun is vastly larger than anything in our daily experience, it accurately places the Sun in the lower middle portion of the stellar size distribution. Sirius A, the brightest star visible in Earth's night sky, is about 1.7 times the diameter of the Sunday. It is the brightest star in our sky, not because it is the largest or most powerful, but because it is one of the closest, sitting just 8.6 light-years away. In absolute terms, Sirius A produces roughly 25 times as much light as the Sun, but there are stars that outshine it by factors of thousands. Moving further up the size scale, we encounter Pollux, a star about 34 light-years from Earth. Pollux is a red giant, a class of star that has exhausted the hydrogen fuel in its core and begun burning hydrogen in a shell surrounding it. This change in internal structure causes the outer layers to expand dramatically. Pollux has swelled to about 9 times the diameter of the Sun, reaching a width of roughly 12 million kilometers. It is cooler at its surface than the Sun, which gives it a more orange-red color, but it still radiates about 33 times as much total light. Red giants represent a late stage in stellar evolution, and in about 6 billion years, the Sun will go through this same transformation. When it does, its outer layers will expand to a size that will likely engulf Mercury and Venus. Whether Earth survives depends on competing factors: how fast the Sun loses mass as it expands, which would cause Earth's orbit to drift outward, versus how quickly the Sun's expanding envelope reaches Earth's current orbital distance. Current models suggest the outcome is genuinely uncertain, and the question remains an active area of research in stellar astrophysics. Arcturus is another giant star worth examining, located 37 light-years from Earth and one of the brightest objects in our night sky. It has a diameter of approximately 18 million kilometers. You could line up about 25 suns side by side across Arcturus's middle. What is unusual about Arcturus is its trajectory through the galaxy. Unlike most stars in the Sun's neighborhood, Arcturus is not part of the Milky Way's main disk population. Its velocity, direction, and chemical composition all suggest it originated in a smaller galaxy that was absorbed by the Milky Way billions of years ago. It is passing through the galactic disk as a visitor from a destroyed predecessor galaxy, carrying the chemical signature of an environment that no longer exists. Arcturus emits about 215 times more total energy than the Sun, much of it in the infrared portion of the spectrum. Its surface is cool enough that a significant fraction of its radiation is heat rather than visible light. But even Arcturus looks modest when placed beside the class of stars known as red supergiants. The most famous of these, from our perspective on Earth, is Betelgeuse, the distinctive orange-red star marking the shoulder of the constellation Orion. Betelgeuse is approximately 700 times the diameter of the Sunday. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Mars and potentially reach into the asteroid belt or toward Jupiter, depending on the current size estimate, which varies because Betelgeuse is not a perfectly uniform sphere. It pulses and fluctuates as its outer layers are continuously churned by massive convection cells, each one larger than the entire Sunday. Betelgeuse is near the end of its life. It has burned through its core hydrogen long ago and has since fused progressively heavier elements in successive shells. Currently, it is believed to be fusing oxygen and neon in its core region. The endpoint of this process is a core composed primarily of iron. Iron is significant because fusion of iron does not release energy. Instead, it requires energy input. When an iron core builds up in a massive star, fusion effectively halts, and the core undergoes a sudden gravitational collapse in a fraction of a second, triggering a catastrophic explosion called a core collapse supernova. In 2019, Betelgeuse dimmed dramatically, dropping to about 60% of its typical brightness over the course of a few months. This triggered widespread speculation that the supernova might be imminent. Subsequent analysis revealed the cause was a large surface mass ejection that propelled a cloud of gas and dust outward, temporarily blocking a portion of Betelgeuse's light. When the dust literally cleared, the star returned to closer to its normal brightness. When Betelgeuse does finally explode, and it will, the event will be visible from Earth in daylight for weeks. At its peak, it may be nearly as bright as the full moon. The explosion will be visible to the naked eye from hundreds of light years away. Betelgeuse is roughly 700 light years from Earth, which means the light we see from it left the star around 1300 years ago. It is entirely possible that the explosion has already occurred, and the light from it simply has not reached us yet. Even so, Betelgeuse is not the largest known star. That distinction belongs to a star called Stephenson 218, located roughly 19,000 light-years from Earth in the direction of the constellation Scutum. Stephenson 218 is a red hypergiant. Its diameter is approximately 2,150 times that of the Sunday. In actual measurements, that corresponds to a width of about 3 billion kilometers. If it were placed at the center of our solar system, its outer edge would extend well past Saturn's orbit, swallowing Mercury, Venus, Earth, Mars, Jupiter, and Saturn entirely. The distance from the Sun to Saturn is roughly 1.4 billion kilometers. Stephenson 218 exceeds that by a substantial margin. In the 12-centimeter Earth comparison we have been using, Stephenson 218 would be a sphere about 28 kilometers across. That is taller than 3 Mount Everests stacked on top of each other. If you attempted to circumnavigate Stephenson 218's surface in a commercial aircraft traveling at 900 kilometers per hour, the journey would take approximately 1,500 years. You could fit nearly 10 billion suns inside its volume, or equivalently, roughly 13 quadrillion Earths. Despite this extraordinary size, Stephenson 218 emits approximately 500,000 times more light than the Sunday. That is 500,000 times the Sun's luminosity, yet it remains invisible to the naked eye from Earth because of its distance. Stars of this size exist at the absolute upper limit of what stellar physics permits. The internal pressure generated by nuclear fusion in their cores must balance against the inward pull of their own gravity. At extreme masses, this balance becomes increasingly precarious. Hypergiants shed enormous amounts of mass through powerful stellar winds, and this mass loss limits how large they can grow. Stephenson 218 is thought to be losing mass at a prodigious rate and will not remain in its current state for long in astronomical terms. We have now reached the top of the stellar size hierarchy, but the universe contains objects larger than any star, and they are of a fundamentally different nature. Black holes are regions of space where gravity has become so intense that not even light can escape. Their physical size is measured by the event horizon, the boundary beyond which no information can return. The diameter of the event horizon scales directly with the mass of the black hole. The more massive the black hole, the wider the event horizon. The most massive black holes in the universe are called ultramassive black holes, and they reside at the centers of the most massive galaxies. TON 618 is one of the most extreme examples known. It sits approximately 10 billion light-years from Earth, embedded in the center of a quasar, which is an extremely luminous galaxy core powered by the intense energy released as material falls into the central black hole. TON 618 has a mass of approximately 66 billion solar masses. Its event horizon has a diameter of roughly 1,200 astronomical units, where 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. That means the event horizon of TON 618 is about 40 times as wide as the entire solar system, measured from the Sun to the outermost edge of the Oort cloud in diameter terms. In absolute distance, its event horizon stretches approximately 180 billion kilometers across. In the 12-centimeter Earth scale, TON 618's event horizon would be about 3,760 kilometers wide. For context, the actual Moon has a diameter of about 3,474 kilometers. So on our hypothetical scale, this black hole's event horizon is close to the size of our real Moon. TON 618 is also extraordinarily luminous. The quasar it powers shines with the light of approximately 100 trillion stars. Because material spiraling into the black hole is accelerated and heated to extreme temperatures before crossing the event horizon, releasing an enormous amount of radiation in the process. This makes TON 618 one of the brightest objects in the observable universe, detectable across 10 billion light-years of space. But even TON 618 is not the largest black hole known. Phoenix A star, located in the Phoenix cluster of galaxies roughly 5.8 billion light-years from Earth, has an event horizon with a diameter of approximately 590 billion kilometers. On our 12-centimeter Earth scale, that translates to an event horizon about 5,500 kilometers across, close to the diameter of the actual planet Mars. Phoenix A star is estimated to have a mass of approximately 100 billion solar masses, 1 followed by 11 zeros. The puzzle this raises is one of the genuinely unresolved questions in modern astrophysics. How did an object of this mass form in the available time since the Big Bang? Standard models of black hole growth involve a black hole seeded by the collapse of a massive star, which then grows by swallowing surrounding gas and merging with other black holes over billions of years. But the rate of growth required to reach 100 billion solar masses through that mechanism alone may exceed what the age of the universe allows. One active hypothesis is that some black holes formed not from the collapse of stars, but from dense regions of matter in the very early universe, before stars had formed at all. These hypothetical objects are called primordial black holes. If they exist, they would have started out massive and grown from there, potentially explaining extreme cases like Phoenix A star. This remains an unconfirmed hypothesis, and ongoing surveys of the early universe with new observatories are testing whether the conditions for primordial black hole formation actually existed. Black holes, however enormous, are still discrete objects. The universe also contains structures assembled from thousands of galaxies, and these structures are the largest things of all. The Milky Way itself is a spiral galaxy roughly 100,000 light-years in diameter. It contains somewhere between 100 billion and 400 billion stars. Our solar system is located in the Orion Cygnus Arm, one of several spiral arms extending from the galactic center, positioned about 26,000 light-years from the center. 1 light-year is the distance light travels in a year. Light moves at approximately 300,000 kilometers per second. In a year, light covers about 9.5 trillion kilometers. 100,000 light-years, the diameter of the Milky Way, is therefore about 950 quadrillion kilometers. If Earth were 12 centimeters wide, the Milky Way would span a distance of roughly 15 billion kilometers, approximately the distance from the Sun to the outer edge of the solar system. The galaxy would not fit in any visualization at the scale we have been using. Andromeda, our nearest large galactic neighbor, is approximately 2.5 million light-years away and spans about 220,000 light-years in diameter, making it roughly twice as wide as the Milky Way. The two galaxies are approaching each other and are expected to merge in approximately 4.5 billion years. The merger will be a slow and gradual process rather than a violent collision. Individual stars are too widely spaced to collide with each other, but the two black holes at the galaxy's centers will eventually spiral together over an extended period. The Milky Way and Andromeda are both members of a collection of galaxies called the Local Group, which contains more than 50 galaxies total. The Local Group, in turn, is part of a much larger structure called the Virgo supercluster, which contains thousands of galaxies and stretches roughly 110 million light-years across. And the Virgo supercluster itself is part of an even larger assembly called Laniakea, a supercluster containing more than 100,000 galaxies, with a total mass of roughly 100 million billion solar masses. But even Laniakea is not the largest structure that has been identified. IC 1101 is a galaxy worth stopping on for a moment before we go further. It is an elliptical galaxy located about 1 billion light-years from Earth, and it is among the largest individual galaxies known. Its diameter is approximately 4 million light-years, roughly 40 times the diameter of the Milky Way. It is thought to have grown to this size through repeated mergers with other galaxies over billions of years. At its center sits one of the most massive known black holes, with estimates suggesting a mass of several tens of billions of solar masses. IC 1101 is a glimpse of what can happen when galaxies accumulate at the centers of large clusters over cosmic time. At even larger scales, galaxies are not randomly distributed through space. They form along filaments and sheets of dark matter and gas, with vast empty regions called voids between them. The overall pattern is sometimes described as a cosmic web. Superclusters lie along these filaments, connected to one another by bridges of galaxies and separated by voids that can be hundreds of millions of light years across. Among the largest identified structures within this web is a filament known as Quipu. It stretches approximately 1.3 billion light years in length and contains an estimated mass equivalent to 200 quadrillion suns. For reference, a quadrillion is 1 million billion, written as a 1, followed by 15 zeros. 200 quadrillion is a 2, followed by 17 zeros. Quipu is composed of interconnected galaxy clusters linked by threads of gas and dark matter, forming a branching, rope-like shape. Scientists estimate it contains the equivalent of roughly 13,000 Milky Way galaxies. To place Quipu in the 12-centimeter Earth comparison, the structure would be about 20 light-years long. 20 light-years at the scale where Earth is 12 centimeters. That is a number that has no useful human-scale analogy. We have moved far beyond the territory where scale comparisons remain meaningful to the senses. Whether Quipu qualifies as a single gravitationally bound structure or a loose collection of structures that happen to be spatially associated is a question scientists are still working through. The distinction matters because cosmological models make predictions about how large a gravitationally bound structure can grow in the time available since the Big Bang. If Quipu is genuinely gravitationally bound, it sits at or near the theoretical upper limit. And then there is the Hercules Corona Borealis Great Wall. This structure was first reported in 2013 based on the spatial clustering of gamma-ray bursts, which are the brightest individual events in the universe, visible across billions of light years. A statistical excess of gamma-ray bursts was detected in a particular region of sky, suggesting that an unusually dense region of galaxies occupies that volume of space. The structure that emerged from this analysis spans approximately 10 billion light-years in its largest dimension. 10 billion light-years. The observable universe has a radius of approximately 46 billion light-years, meaning the Hercules Corona Borealis Great Wall stretches across roughly 10% of the entire observable universe. This is the point where cosmological theory faces a serious challenge. The standard model of cosmology, built on decades of observation and theory, includes a principle called large-scale homogeneity. On the largest scales, the universe is expected to look roughly the same in all directions and at all points. There should be no regions that are dramatically overdense or underdense compared to the average. The scale at which this homogeneity kicks in is generally estimated to be somewhere around 300 to 500 million light-years. The Hercules Corona Borealis Great Wall is between 10 and 30 times larger than that threshold, depending on how you measure it. A structure this large should not, according to standard cosmological models, have had time to assemble itself since the Big Bang. Gravity works, but it works slowly, pulling together enough matter across 10 billion light-years to form a coherent structure requires more time than the universe has so far existed, if our current models of cosmic growth rates are correct. The researchers who identified the structure were explicit about this. They stated that its existence is in tension with the standard cosmological model, not a minor tension, a substantial one. Several interpretations remain open. One is that the gamma-ray burst clustering that served as the evidence for the structure reflects a statistical fluctuation rather than a true physical overdensity of galaxies. Gamma-ray bursts are rare events, and mapping large-scale structure through them introduces uncertainties that direct galaxy surveys would not. Follow-up studies examining the region have produced mixed results, with some supporting the existence of an overdensity and others being less conclusive. A second possibility is that the Hercules Corona Borealis Great Wall is real, but is not actually a single gravitationally bound structure. It may be a large region of connected but loosely associated galaxy filaments that appear as a coherent unit when viewed in projection, but are in reality a more loosely coupled assembly. If the structure is not gravitationally bound, the theoretical constraints on how large it can be are less stringent. A third possibility, the most consequential scientifically, is that the standard cosmological model is incomplete. If a truly coherent structure of this size exists, it would require either a revision to the model of how density fluctuations from the early universe seeded large-scale structure, or some other modification to our understanding of how the universe has evolved. The Hercules Corona Borealis Great Wall, if confirmed at its full scale, would be one of the most significant observational challenges to the current cosmological framework. What makes this especially interesting from a scientific standpoint is the timescale involved. The light we observe from this region has been traveling for billions of years. We are looking at these structures not as they are now, but as they were when that light was emitted. The universe has continued to evolve during the journey of that light, and what we observe is a historical snapshot, not a current map. Reconstructing three-dimensional structure from these observations requires careful statistical methods and assumptions about how the universe has changed. Upcoming large-scale surveys, including those planned with new wide-field telescopes currently being commissioned, will map galaxy distributions across vast volumes of space with unprecedented precision. These surveys will either confirm or challenge the existence of the Hercules Corona Borealis Great Wall by providing direct galaxy counts rather than gamma-ray burst proxies. The results will be a significant test of how well our current cosmological models hold up at the largest observable scales. There is a recurring pattern in astronomy worth noting here. Every time observation technology advances, the universe reveals structures larger than previously known. When early telescopes revealed that the Milky Way was not the whole of the universe, the scale of reality expanded dramatically. When surveys of galaxy distributions revealed filaments and voids, the scale expanded again. Each advance has pushed the boundary of what we classify as a structure and how we understand the universe to be organized. The detection of the cosmic microwave background in the 1960s confirmed that the universe has a finite history, beginning approximately 13.8 billion years ago in a hot, dense state. Since then, the universe has expanded and cooled, and gravity has been slowly pulling matter together into increasingly complex structures. The largest structures we observe represent the culmination of that entire process, operating over the full age of the universe. What the Hercules Corona Borealis Great Wall, if it is real at its reported scale, would suggest is that either structure formation began earlier than we think, or progressed faster than our models predict, or both. Both possibilities have implications for the nature of dark matter, which provides the gravitational scaffolding along which ordinary matter assembles, and dark energy, which is driving the accelerating expansion of the universe, and which is expected to eventually slow and halt the further growth of large-scale structure. Understanding why the universe is structured the way it is at the largest scales requires understanding the interplay between these two poorly understood components. Dark matter and dark energy together account for approximately 95% of the total energy content of the universe, yet neither has been directly detected in a laboratory. What we know about them comes almost entirely from their gravitational effects on the structures we observe. The largest objects in the universe are therefore not just impressive in a descriptive sense. They are diagnostic tools. Their sizes, shapes, and distributions encode information about the physics of the early universe, about the nature of dark matter and dark energy, and about whether our current theoretical framework captures the full picture of how cosmic structure forms. From a single grain of sand on a beach, to a planet, to a star, to a galaxy, to a supercluster stretching 1 billion light years, to a great wall spanning 1/10 of the observable universe, each step up in scale reveals a universe that is more organized, more connected, and more surprising than the step before it. The structures we have discussed represent the full range of what observation has so far made available, but the history of astronomy suggests that as observation improves, the inventory will expand. There are likely structures beyond the current observational horizon, patterns in the distribution of matter that we cannot yet see. And within the structures we have identified, many fundamental questions remain open. How did the most massive black holes grow to their current sizes so quickly? What seeded the initial density fluctuations that eventually produced galaxy clusters and superclusters? Why does the large-scale structure of the universe show the particular pattern it does? And does that pattern extend uniformly in all directions at sufficiently large scales? These are not purely academic questions. They sit at the intersection of the largest and the smallest scales of physical reality. The largest structures in the universe grew from quantum scale fluctuations in the first fractions of a second after the Big Bang, fluctuations so tiny that quantum mechanics is required to describe them. The pattern of today's universe is a magnified imprint of physics, operating at energies and densities we cannot reproduce in any laboratory. What we observe when we map the cosmic web, when we identify filaments and voids and great walls, is the universe's own record of its earliest moments, written across billions of light years of space in the language of galaxies. We are still learning to read it. Scientists working on the next generation of large-scale structure surveys are developing methods to extract increasingly precise information from galaxy distributions. These include measurements of the subtle distortions in galaxy shapes, caused by the gravitational lensing effect of intervening matter, statistical analyses of the clustering of galaxies at different scales, and measurements of the way galaxies move toward or away from us as tracers of the underlying density field. Each of these techniques provides a different window into the same underlying structure. Together, they should allow much more precise tests of whether features like the Hercules Corona Borealis Great Wall are genuine anomalies requiring new physics, or whether they fall within the range of fluctuations that standard models permit. The story of the universe's largest objects is, in the end, a story about the limits of our knowledge at any given moment. Every structure on this list was unknown a century ago. Some were unknown a decade ago. The universe has consistently turned out to be more intricate, more varied, and more extreme than any prior model predicted. That record does not prove that the next observation will reveal something equally surprising, but it suggests that the present picture is unlikely to be the final one. What we can say with confidence is that the universe operates at scales our intuitions were never designed to process. The tools of mathematics and observation extend our reach far beyond what unaided perception allows. And at every scale we have managed to probe, we find that the universe has been busy doing exactly what physics predicts it should, while occasionally doing something that physics did not predict at all. Those occasions are where the most interesting science happens, and we have not yet run out of them. To understand why scale in the universe matters beyond simple record keeping, it helps to think about what structures are actually telling us. When astronomers map out a supercluster, or trace the outline of a cosmic filament, they are not simply cataloging scenery. They are measuring the outcome of processes that began nearly 14 billion years ago, and have been operating continuously ever since. The size of a structure is a record of how much time and energy have gone into building it. Consider how structure emerged in the first place. In the moments after the Big Bang, the universe was extraordinarily uniform. The temperature and density of matter were nearly identical everywhere, but not exactly identical. Quantum mechanics, which governs behavior at the smallest scales, introduces inherent uncertainty into physical quantities. In the extreme density of the early universe, these quantum fluctuations produce tiny variations in density, regions where matter was very slightly more concentrated than the average, and regions where it was very slightly less. These fluctuations were minuscule. The fractional overdensity in any given region was roughly 1 part in 100,000 compared to the average. If you could have measured the density of the universe at 1 billion different locations in its first seconds of existence, the variation between measurements would have been a difference in the 5th decimal place. But gravity is patient. Over hundreds of millions of years, regions that were even slightly denser than average began attracting more matter from their surroundings. As more matter accumulated, the gravitational pull increased, pulling in more matter still. The process was slow at first, then increasingly rapid. Regions of slight overdensity became filaments and sheets of matter. Regions between them became emptier as matter drained toward the overdense regions. What started as a smooth, nearly featureless sea of matter gradually organized itself into the elaborate structure we observe today. The pattern that emerged is not random. It reflects the specific statistical properties of the initial fluctuations, which in turn reflect the physics of the early universe. Theoretical models of those early conditions make precise predictions about what the large-scale distribution of galaxies should look like today. Comparing those predictions to observations is one of the most powerful tests of our understanding of fundamental physics. This is why the detection of a structure like the Hercules Corona Borealis Great Wall carries such theoretical weight. The models predict that structure grows hierarchically. Small clumps form first, then combine into larger structures, which combine further, and so on. The process has a characteristic timescale. It takes a certain amount of time for gravity to pull together a cluster of galaxies, and longer still to assemble a supercluster, and longer still to build a structure spanning billions of light years. If a structure appears to be larger than what the available time allows, it is not simply surprising in the way that a particularly large mountain is surprising. It is a potential signal that something about the underlying physics is different from what we assumed. The sensitivity of large-scale structure to the underlying physics is one of the reasons why cosmologists have devoted so much effort to mapping it. The Sloan Digital Sky Survey, which began collecting data in the year 2000, mapped the positions of hundreds of millions of galaxies across a large fraction of the sky, and revealed the cosmic web in unprecedented detail. It showed clearly that galaxies cluster along filaments that these filaments form walls and sheets surrounding vast empty voids, and that the pattern is consistent across different regions of the sky, which is evidence in favor of the assumption of large-scale homogeneity. But the surveys also found tantalizing anomalies. The Sloan Great Wall, discovered in 2003, was at the time the largest known structure, stretching roughly 1.4 billion light-years. The discovery came from the same dataset that confirmed the cosmic web's existence. Shortly afterward, the discovery of the Hercules Corona Borealis Great Wall pushed that scale by nearly an order of magnitude to 10 billion light-years. Each time the observational frontier expands, the catalog of extreme structures grows, and each new addition raises the same question. Is this within the expected range of variation, or is something fundamentally different going on at these scales? The mathematical framework used to analyze these questions is called the power spectrum of density fluctuations. It describes how much structure exists at each spatial scale, from tiny separations to the largest observable distances. The predictions of the standard cosmological model for this power spectrum have been tested extensively and match observations across a wide range of scales with impressive precision. The current challenge is at the very largest scales, where the number of independent observational volumes is small, by definition. There is only one observable universe. At scales approaching the entire observable universe, statistical analysis becomes difficult because there are simply not many independent samples of the universe to compare. This is sometimes called cosmic variance. No matter how good your telescope or how precise your catalog, you cannot reduce the uncertainty below a certain level at the very largest scales, because you are working with a sample of one. This is one reason why the interpretation of the Hercules Corona Borealis Great Wall remains contested. The evidence for its existence is based on a clustering signal in gamma-ray burst positions. Gamma-ray bursts are detected in the distant universe, but their occurrence rate is low enough that mapping large-scale structure through them introduces statistical challenges. A direct galaxy survey of the same region would provide more robust evidence, but has not yet been completed at the relevant depth. Future observatories, including the Vera C, Rubin Observatory currently undergoing commissioning in Chile, the Square Kilometre Array Radio Telescope being assembled in South Africa and Australia, and the Nancy Grace Roman Space Telescope in orbit, are expected to dramatically increase the precision and volume of galaxy surveys over the coming decade. These instruments will map galaxy distributions to much greater distances and with much finer detail than previous surveys, providing definitive tests of whether structures like the Hercules Corona Borealis Great Wall fall within or outside the predictions of the standard model. If the structure is confirmed at its claimed scale, the implications would extend well beyond cosmology. A structure spanning 10 billion light-years that cannot have formed through standard gravitational processes in the time since the Big Bang would require some modification to the physics of structure formation. The candidates include modifications to the properties of dark matter, which in standard models is assumed to be cold, meaning it moves slowly and clusters on small scales first before larger structures assemble. Warmer dark matter, which moves faster, would suppress small-scale structure while potentially allowing rapid large-scale assembly under certain conditions. Other candidates include modifications to the theory of gravity itself at large scales, or the presence of additional fields or forces operating in the early universe that are not captured by the current framework. None of these alternatives is favored by existing data as a whole. The standard model with cold dark matter has passed so many observational tests that abandoning it would require extremely compelling evidence. But the science is honest about where it is uncertain, and the very largest scales of the observable universe remain an area where that honesty matters. There is something clarifying about thinking through the chain of scales we have traced. At the smallest end of our journey are rocky planets like Earth. Earth itself feels vast from any human vantage point. Its surface covers about 510 million square kilometers. Its deepest ocean trench descends nearly 11 kilometers below sea level. Its highest mountains reach nearly 9 kilometers above it. The total diameter is just under 12,700 kilometers. Jupiter's diameter is about 11 times Earth's. Stephenson 218's diameter is about 169 million times Earth's. The Milky Way, expressed in the same Earth diameter units, is roughly 7.5 billion times Earth's diameter. The Hercules Corona Borealis Great Wall, if its claimed dimensions are accurate, is approximately 7.5 trillion times the diameter of Earth. The ratio between the smallest rocky planet and the largest known cosmic structure is a number with 13 digits. This is the range of scales across which structure in the universe operates. It is a range that no single physical law governed from start to finish. Rocky planet formation is understood using solid-state physics and fluid dynamics. Stellar structure is understood using nuclear physics and radiation transport. Galaxy formation involves gravitational dynamics and gas physics. Large-scale structure formation involves general relativity and the statistics of the early quantum universe. Each domain of scale has its own physics, its own timescales, its own characteristic objects, and yet they are all connected. The iron in Earth's core was forged in the cores of stars that exploded billions of years ago before the sun existed. The sun formed from the remnants of those explosions, mixed with primordial hydrogen and helium from the Big Bang. The sun sits in a galaxy that assembled over billions of years under the influence of dark matter that was seeded in the first fractions of a second of the universe's existence. Every atom and every object we have discussed traces its origin back to processes operating across this entire chain of scales. The largest objects we can observe are not disconnected from the smallest. They are the cumulative result of physics operating across every scale in between, linked together by time and gravity and the initial conditions set at the universe's beginning. Understanding that chain is one of the central projects of modern astrophysics. It requires instruments that can measure objects ranging from nearby asteroids to galaxies at the edge of the observable universe. It requires theoretical frameworks that span quantum field theory, general relativity, and statistical mechanics. It requires patience, because many of the key observations take years or decades of telescope time to accumulate enough data for meaningful conclusions. And it requires a willingness to sit with uncertainty. Science does not always know the answer. In the case of the Hercules Corona Borealis Great Wall, science genuinely does not know whether the structure is what it appears to be. The measurement exists. The theoretical tension it creates is real. What it means is not yet resolved. That is not a failure. That is the working edge of knowledge, where the most important questions live. The history of measuring cosmic structure is full of moments where an observation forced a revision of the prevailing model, and each revision led to a deeper and more precise understanding of how the universe works. The discovery that distant galaxies are receding from us, and that the more distant ones are receding faster, led to the conclusion that the universe is expanding. The further discovery that the expansion is accelerating led to the inference that some form of dark energy, with properties unlike any known substance, permeates all of space. The discovery that the early universe was nearly uniform, combined with the observation that today's universe is highly structured, constrained the initial density fluctuations to remarkably precise values. Each of these discoveries came from taking measurements seriously, even when they did not fit the prevailing expectation. The willingness to update the model in response to data, rather than dismissing the data when it is inconvenient, is what allows science to make genuine progress on questions of this scale. The question of how large the largest structures in the universe actually are is more than a matter of curiosity. It is a diagnostic probe of the physical laws that govern the universe from its first moments. The structures we see today are answers to questions we can ask with our instruments. What we have learned so far is that the universe is organized, that the organization follows knowable physical laws, and that the range of scales across which those laws operate is far larger than any earlier framework anticipated. There are stars like Stephenson 218 that dwarf the entire inner solar system. There are black holes whose event horizons are wider than the distance from the sun to the outer planets. There are galaxy clusters whose total mass is millions of times the mass of the Milky Way. And there are filaments and walls connecting those clusters into structures spanning a significant fraction of the observable universe. What exists beyond the observable universe is, by definition, beyond our current reach. The observable universe is bounded not by the physical edge of space, but by the distance light has been able to travel since the Big Bang. Beyond that horizon, space almost certainly continues. Whether it continues uniformly, or whether it contains structures different from anything in our observable volume, is an open question that may remain open for a very long time. But within the volume we can see, the inventory is already extraordinary. From the first rocky planet to the widest cosmic wall, from the brightest quasar to the darkest void, the universe has filled its available space with structure at every scale. And at each scale, the structures are not just passively sitting there, they are evolving. Stars are forming and dying, black holes are growing, galaxies are merging, clusters are assembling. The cosmic web is still being drawn. We are observing this process from a single location at a single moment in the universe's history. with instruments that have existed for less than a century. The fact that we have already traced structure from planets to billion light-year walls is, from a certain perspective, astonishing. The fact that significant questions remain at every scale is not discouraging. It is the reason the work continues. The universe has not run out of things to show us. It is larger than our models have sometimes assumed, more structured than expected at some scales, and more uniform than expected at others. It has produced objects like Phoenix A star and Stephenson 218 that sit at the theoretical limits of what physics permits, and possibly objects like the Hercules Corona Borealis Great Wall that may sit beyond those limits. Every one of those extremes is a data point. Every data point is a constraint on theory, and every successfully constrained theory is a step toward understanding why the universe, starting from a nearly featureless quantum state nearly 14 billion years ago, ended up looking exactly like this. That question does not have a final answer yet, but the measurements keep coming, and they keep being surprising, and that is precisely what makes the science worth doing. There is a detail about stellar structure that rarely gets discussed outside of research papers, but that turns out to be central to understanding why stars have the sizes they do. It comes down to the competition between two forces that are constantly in tension inside every star, from the smallest red dwarf to the largest hypergiant. On one side is gravity. Every atom in a star is pulling on every other atom, and the net effect of all that pulling is an inward force that would collapse the star if nothing opposed it. Left to its own devices, a cloud of hydrogen gas will indeed collapse under its own gravity. That collapse is how stars form in the first place. But once nuclear fusion ignites in the core, the energy released pushes outward, creating radiation pressure and thermal pressure that fight back against the inward pull. For most of a star's life, these two forces balance almost perfectly. The technical term is hydrostatic equilibrium. This balance is self-regulating in a way that makes stars extraordinarily stable. If the core gets slightly hotter, fusion rates increase, more energy is released, the increased pressure expands the core slightly, the expansion cools the gas, fusion rates drop back down, and the balance is restored. If the core cools slightly, the reverse happens. Stars are thermostats. What sets the maximum size a star can reach is a limit on this balance. As stars grow more massive, the radiation pressure produced by their fusion cores becomes increasingly dominant. Photons are particles of light, and they carry momentum. When fusion is intense enough, the pressure of the outflowing photons can overwhelm the inward gravitational pull and begin blowing material off the star's surface. This mass loss rate increases steeply with stellar mass and luminosity. There is a theoretical boundary called the Eddington limit, which marks the point at which radiation pressure exactly balances gravity for material at the star's surface. Above this luminosity, radiation pressure should blow material away faster than the star can hold it. For stars approaching this limit, mass loss becomes catastrophic. The most massive stars known are all losing mass at rates many orders of magnitude higher than the Sun. And this mass loss is what prevents any star from growing arbitrarily large. Stephenson 218 is a red hypergiant, and its very large size is related to this dynamic in an indirect way. Red hypergiants are not the most luminous stars, and they are not the most massive. They have expanded to their enormous sizes precisely because, at their current stage of evolution, the balance between radiation pressure and gravity has tipped in a direction that causes the outer layers to swell dramatically. The interior temperature drops as the outer envelope expands, shifting the star's color toward red, while the increased surface area means the total luminosity increases even though the surface temperature decreases. This is the same principle behind red giants like Pollux, just taken to an extreme degree. The underlying physics is the same: exhaustion of core hydrogen fuel, transition to shell burning, and dramatic outer envelope expansion. In Stephenson 218, this process has produced an object so large that it is genuinely difficult to measure precisely. Stars of this class are not well-defined spheres. They have diffuse, extended outer atmospheres that merge gradually into the surrounding interstellar medium. The boundary of the star is not a sharp surface, but a zone. This fuzziness in the definition of a star's edge is worth dwelling on for a moment. When we say Stephenson 218 has a diameter of roughly 3 billion kilometers, we are choosing a particular definition of what counts as the surface. For many purposes, astronomers use the photosphere, which is the layer at which the material becomes optically thin, meaning light can escape directly into space from that layer rather than being scattered or absorbed. But for hypergiants with extended dynamic outer atmospheres, even defining the photosphere precisely is challenging because the atmosphere varies significantly in density and temperature as a function of time and position. The same definitional challenge applies to black holes, though in a very different way. An event horizon is a precise mathematical boundary in the theory of general relativity. It is not fuzzy in the way a stellar photosphere is. But what makes measuring a black hole's size complicated is that the event horizon is, by definition, invisible. No light escapes from within it, so the event horizon itself cannot be imaged directly. What can be imaged is the shadow it casts against the bright material orbiting it, which is how the Event Horizon Telescope produced the first image of a black hole's central region. For the black hole at the center of the galaxy, Messier 87 in 2019. That black hole, known as Messier 87 star, has a mass of approximately 6.5 billion solar masses. Its event horizon has a diameter of roughly 38 billion kilometers. The Event Horizon Telescope, which is an array of radio telescopes spread across multiple continents working together as a single Earth-sized instrument, resolved the central shadow at a scale of about 40 microarcseconds. An arcsecond is 1/3600th of a degree. A microarcsecond is 1/millionth of that. The angular resolution achieved was equivalent to imaging a coin on the surface of the moon from Earth. Phoenix A star, the largest black hole we discussed, has not yet been directly imaged. Its event horizon of approximately 590 billion kilometers would subtend a larger angle on the sky in absolute terms. But it is also much more distant, at about 5.8 billion light-years, which makes the angular size accessible to observation much smaller. Direct imaging of Phoenix A star would require an instrument far beyond current capabilities. What we know about it comes from the X-ray emission of the surrounding cluster gas, from which the mass can be estimated using the physics of gas dynamics and equilibrium. This is a recurring theme in the study of the universe's largest objects. Most of what we know about the most extreme objects comes not from direct measurement of the objects themselves, but from the effects they have on their surroundings. A black hole's mass is inferred from the motions of stars and gas around it. A galaxy's dark matter halo is inferred from the orbital velocities of stars and satellite galaxies. A supercluster's total mass is inferred from gravitational lensing of background objects. The universe reveals its most extreme structures indirectly, through signatures impressed on nearby material. This indirection is not a limitation in the derogatory sense. It is how inference works in science, when direct access is impossible. Geologists infer the composition of Earth's core from seismic waves, because no drill can reach it. Particle physicists infer the properties of short-lived particles from the debris they leave in detectors. Cosmologists infer the properties of black holes from the gravitational effects on surrounding matter. The indirection does mean that all measurements of the universe's largest objects carry uncertainties that direct measurements would not. The mass of Phoenix A star, for example, is known to within perhaps a factor of 2 or 3. Whether its mass is 50 billion solar masses or 150 billion solar masses would change how we think about its formation. But current measurements cannot distinguish between these possibilities with high confidence. Better X-ray observatories, particularly those planned for launch in the coming decades, will reduce these uncertainties significantly. Similarly, the diameter of the Hercules Corona Borealis Great Wall is uncertain enough that characterizing it as 10 billion light-years versus, say, 6 billion light-years would substantially change how it compares to theoretical predictions. The difference matters for the theoretical interpretation. A 6 billion light-year structure, while still extremely large, might fall within the tail of what standard models permit. A 10 billion light-year structure more decisively sits outside that range. Getting the measurement right is not a minor refinement. It is the question that determines whether a theoretical anomaly exists. This situation is scientifically productive precisely because it is unresolved. An open question with clear paths toward resolution is one of the most valuable things science can have. The paths toward resolution in this case are concrete. Better galaxy surveys, improved gamma-ray burst statistics, and more refined theoretical models of structure formation will between them either confirm or dissolve the apparent anomaly within the next decade or two. In the meantime, there are other aspects of the universe's size hierarchy that deserve attention, particularly the question of how the objects we have discussed relate to the overall inventory of the universe's mass and energy. Of all the mass and energy in the observable universe, ordinary matter, the kind made of protons, neutrons, and electrons that makes up stars, planets, gas clouds, and everything we can directly detect, accounts for only about 5%. The remaining 95% is divided between two poorly understood components. Roughly 27% is dark matter, and approximately 68% is dark energy. Dark matter earns its name because it does not emit, absorb, or scatter light at any wavelength. It interacts with ordinary matter only through gravity. It was first proposed in the 1930s by Fritz Zwicky, who noticed that galaxies in the Coma cluster were moving too fast to be held together by the visible mass alone. Since then, evidence for dark matter has accumulated from multiple independent sources: galaxy rotation curves, gravitational lensing, the cosmic microwave background, and the large-scale distribution of galaxies. Dark matter plays a critical role in the formation of large-scale structure. In the early universe, dark matter density fluctuations grew faster than ordinary matter fluctuations, because dark matter does not interact with radiation, and therefore does not experience the radiation pressure that resisted the growth of ordinary matter. Clumps. Dark matter built gravitational wells first, and ordinary matter subsequently fell into those wells, eventually forming the stars and galaxies we observe. The filamentary structure of the cosmic web, the web of galaxy clusters and superclusters we discussed, is essentially the skeleton of dark matter. The positions of galaxies trace the positions of dark matter halos, because galaxies form preferentially where dark matter concentrations provided the initial gravitational seed. The voids between filaments are regions of low dark matter density. When we map the distribution of galaxies, we are indirectly mapping the dark matter distribution. This connection between galaxies and dark matter means that the largest structures we observe, like Quipu or the Hercules Corona Borealis Great Wall, correspond to the largest concentrations and filaments of dark matter. Understanding why dark matter is distributed the way it is connects directly to understanding why galaxies are distributed the way they are, which in turn determines what kinds of record-setting structures form. The identity of dark matter remains one of the most important, unresolved questions in physics. Leading candidates include hypothetical particles called WIMPs, weakly interacting massive particles, which have been searched for in underground detectors designed to catch the rare occasion when a dark matter particle scatters off an atomic nucleus. Despite sensitive searches spanning more than 2 decades, no confirmed WIMP detection has been made, which has put pressure on the most popular versions of the WIMP hypothesis and opened the door to alternatives. Other candidates include axions, ultralight particles originally proposed to solve a problem in nuclear physics, and sterile neutrinos, heavier relatives of the standard neutrinos that interact even more weakly. None of these has been confirmed either. The search continues, with new experiments targeting different mass ranges and interaction strengths. What does dark energy contribute to the size story? In a certain sense, dark energy is what sets the upper limit on how large structures can ever become. Dark energy is the name given to the observation that the universe's expansion is accelerating, that distant galaxies are receding from us at an ever-increasing rate. This acceleration was discovered in 1998 by 2 independent teams studying Type 1a supernovae, explosions so consistent in their intrinsic brightness that they can serve as distance markers. Both teams found that the most distant supernovae were fainter than expected, meaning they were farther away than a simple expansion model predicted, meaning the expansion has been speeding up. The implication for large-scale structure is significant. Gravity attracts, dark energy repels, in an effective sense, by causing space itself to expand faster and faster, pulling matter apart over large enough scales. In the early universe, when matter was denser, gravity dominated and structure formation was rapid. But as the universe expanded and the density of matter dropped, dark energy, which does not dilute with expansion, became increasingly important. In the current era, dark energy dominates the universe's energy budget, and its effect is to prevent large-scale structures from continuing to grow. The structures we see today, the galaxies, clusters, and filaments, were assembled during an era when gravity was the dominant force. Future generations, if they exist, will inherit a universe where the largest structures will no longer be growing. The cosmic web has largely finished assembling. The next phase of the universe's history is one of continued expansion, in which individual galaxy groups hold together under their own gravity, but the distances between groups grow without limit. In the very far future, on timescales of trillions of years, even galaxy clusters may be disrupted if dark energy remains constant at its current value, though more extreme scenarios involving phantom dark energy, in which the effective repulsive force grows stronger over time, would cause much more drastic outcomes. In the most extreme version of this scenario, called the Big Rip, dark energy would eventually overcome even the binding force of atoms, tearing apart all structures at every scale. Current measurements do not favor this scenario, but cannot rule it out. These future possibilities are speculative, rooted in extrapolating current measurements into scenarios far beyond what any observation can directly test. But they are not arbitrary. They follow from the physics we know, applied to the conditions we measure, and they represent honest attempts to understand where the current trajectory of the universe leads. What we know with high confidence is the present inventory. A universe roughly 13.8 billion years old, containing galaxies distributed in a filamentary network of dark matter, embedded in an ocean of dark energy, driving accelerating expansion, with structures ranging from rocky planets a few thousand kilometers wide to potential walls 10 billion light years across. Each entry in that inventory was once unknown. Each was revealed by instruments that pushed past the limits of what came before, and each answered some questions while raising new ones. The red hypergiant Stephenson 218 was identified as the largest star only through infrared observations that could penetrate the dust clouds obscuring it. Earlier surveys in visible light missed it, because the same dust that makes it difficult to see also blocks shorter wavelengths. The identification required combining data from multiple infrared observatories, measuring the spectrum of the star to determine its surface temperature, and then calculating its radius from the temperature and luminosity using fundamental equations of stellar physics. Phoenix A star's status as the largest known black hole was established through X-ray observations by space-based telescopes capable of detecting the extremely hot gas concentrated in galaxy clusters. The mass estimate depends on models of how the gas in the cluster should be distributed if the system is in a particular kind of equilibrium, and the reliability of those models is itself an area of active research. TON 618's mass was established through measurements of the width of spectral lines in the light from the surrounding quasar, a technique called reverberation mapping that uses the time delay between brightness variations in the central region and corresponding variations in the surrounding gas to infer the size of the emitting region, and therefore the black hole mass. In each case, the measurement required not just an instrument, but a chain of reasoning that connected raw data to the physical property of interest. That chain is only as strong as its weakest link, and astronomers spend considerable effort testing and strengthening each link. Better measurements of the distance to Stephenson 218 would reduce the uncertainty in its luminosity. Better models of cluster gas dynamics would reduce the uncertainty in Phoenix A star's mass. Better coverage of the quasar's spectral variability would reduce the uncertainty in TON 618's mass. This process of refinement is ongoing and will continue with each new generation of instruments. The list of largest known objects is not permanent. The measurements we have today are the best available today, not final answers carved in stone. Some of the objects on the list will be superseded by newly discovered examples. Some of the size and mass estimates will be revised as better data comes in. The scientific literature regularly updates the record books, and that updating is how progress works. What will not change, even as specific numbers are refined, is the basic picture. A universe organized at every scale, from the smallest rocky world to walls spanning a tenth of all observable space, with the full range of sizes reflecting the full history of physical processes that have operated since the beginning. The largest structure we can observe, and the smallest rocky planet, are connected by a chain of physics 14 billion years long. That chain is what astrophysics is trying to reconstruct, one measurement at a time. The largest objects in the universe are the final chapters of that story. We are still learning how to read them. There is a number that appears in cosmology that almost never gets the attention it deserves, and understanding it changes how the entire scale hierarchy of the universe looks. That number is approximately 380,000 years. For the first 380,000 years after the Big Bang, the universe was opaque. Matter and radiation were coupled together in an almost perfectly smooth, extremely hot plasma. Photons, the particles of light, could not travel freely. They scattered off electrons constantly, bouncing around inside the plasma like light inside a frosted glass sphere. Because the universe was continuously expanding, it was also continuously cooling. At about 3,000 degrees Kelvin, something remarkable happened. The universe became cool enough for protons and electrons to combine into neutral hydrogen atoms. When that happened, there were suddenly no free electrons for photons to scatter off of. In an almost geological sense, the universe went from opaque to transparent in a relatively brief period. The photons that existed at that moment, which was roughly 380,000 years after the Big Bang, were released and have been traveling freely through space ever since. We detect those photons today. They have been traveling for approximately 13.8 billion years, and in that time, the expansion of the universe has stretched them from optical light to microwave radiation. They constitute what we call the cosmic microwave background, and they carry, encoded in their temperature and polarization patterns, a snapshot of the universe as it was at the moment they were released. The cosmic microwave background is extraordinarily uniform. Its temperature across the entire sky varies by only about 1 part in 100,000. But those tiny variations, the slightly hotter and cooler patches, are the direct imprint of the initial density fluctuations we discussed earlier. They are the seeds of everything that came after: galaxies, clusters, filaments, great walls. Every structure in the universe is gravitationally descended from those barely perceptible ripples in the plasma of the early universe. Measuring the cosmic microwave background precisely is one of the most productive activities in modern cosmology. The Planck satellite, operated by the European Space Agency and completing its mission in 2013, produced the most detailed map ever made of the cosmic microwave background, measuring temperature variations to a precision of millionths of a degree across the full sky. From that map, cosmologists extracted estimates of the age of the universe, its composition in terms of ordinary matter, and dark energy, the geometry of space, and the statistical properties of the initial fluctuations. The results were a triumph for the standard cosmological model. The values extracted from the cosmic microwave background matched predictions across a remarkably wide range of tests. The fraction of dark matter agreed with estimates from galaxy rotation curves. The fraction of dark energy agreed with estimates from supernova distance measurements. The geometry of space was consistent with flatness, meaning the universe does not curve back on itself like the surface of a sphere. But there was one tension that the Planck data introduced rather than resolved. When cosmologists used the cosmic microwave background data to predict how rapidly the universe should be expanding today, and then compared that prediction to direct measurements of the expansion rate using nearby objects, the two values did not quite agree. The expansion rate measured locally came out higher than what the cosmic microwave background data predicted. This discrepancy, known as the Hubble tension because the expansion rate is called the Hubble constant, has grown more significant as measurements have become more precise. It is not going away with better data. If anything, better data has made it clearer. Two sets of measurements, each using completely independent methods, each done with the most careful attention to potential systematic errors, give answers that differ by approximately 8 to 10%. In a field where 1% is already noteworthy, 8 to 10% is a loud signal. Several explanations have been proposed. Some involve new physics, such as a form of dark energy that was more intense in the early universe, before becoming the constant we observe today. Some involve modifications to how early universe physics is modeled. Some involve the possibility that the measurements themselves contain unrecognized systematic errors. No single explanation has yet won consensus. The Hubble tension is relevant to the story of large-scale structure because the expansion rate of the universe determines how much time has been available for structures to grow. If the universe is expanding faster than the standard model predicts, then either it is younger than we think, or the model's assumptions about the growth of structure need revision, or both. Getting the expansion rate right is not just about knowing how big the universe is. It is about knowing how much time gravity has had to build the largest structures we observe. This connection illustrates something important about cosmology as a field. The different observations are not independent. The expansion rate, the density of dark matter, the amplitude of the initial fluctuations, and the sizes of the largest structures are all linked through the physics of the standard model. A change in one parameter ripples through predictions for all the others. This makes the field extraordinarily demanding. No single observation can be understood in isolation, and disagreements that seem peripheral turn out to be connected to everything else. The Hubble tension is one of the most actively debated questions in current cosmology. It is being attacked from multiple directions simultaneously. New measurements of the Hubble constant using gravitational waves from merging neutron star pairs, a completely independent method first demonstrated in 2017, are expected to provide an independent cross-check. The Roman Space Telescope will dramatically expand the sample of Type 1, a supernovae used in Hubble constant measurements. New observations of the cosmic microwave background with upgraded instruments will test whether the Planck measurements can be reproduced with different technology. The resolution, when it comes, will either confirm that the standard model just needs a modest adjustment or reveal that something genuinely new needs to be incorporated into our understanding of the universe. Either outcome advances the science. And either outcome will affect how we interpret the sizes and distributions of the universe's largest structures. Because the framework used to interpret those observations is the same framework under tension. Standing back from the specific numbers and considering what the overall picture communicates is worthwhile here. We live on a rocky planet, orbiting a medium-sized star in the outer suburbs of a spiral galaxy. That galaxy is part of a local group of galaxies, which is part of a supercluster, which is part of a cosmic web of filaments and voids. And somewhere in that web, if the observations are confirmed, there is a wall stretching 10 billion light-years across, a structure so large that its existence strains the theoretical framework we use to understand everything else. The human experience of scale has always been local. We evolved to navigate environments measured in meters and kilometers. We learned to engineer on scales up to thousands of kilometers. Modern technology has extended our reach to planetary and stellar scales, and our instruments have extended our perception to the edge of the observable universe. But none of that extension has come equipped with an intuition update. The numbers are available. The understanding of their implications is hard-won and incomplete. The intuition for what it feels like to exist in a universe of this scale is something no human has, and perhaps something no mind evolved for local navigation can fully possess. What we do have is the mathematics, and the observations, and the frameworks we have built to connect them. Those tools are not substitutes for intuition. They are something different, a way of reasoning correctly about things that intuition cannot reach. The largest black holes, the widest galaxies, the longest filaments of the cosmic web are not accessible to any human sense. They are accessible only through the chain of inference that runs from telescope observations through mathematical models to physical conclusions. That chain is imperfect. Every link in it carries uncertainty. Every link is being tested and refined by ongoing observations and theoretical work. The history of the chain is one of progressive improvement. Better instruments, better models, better understanding of systematic errors, better theoretical frameworks. The chain today is more reliable than it was 50 years ago, and less reliable than it will be 50 years from now. What we can say with confidence about the universe's largest objects is this: they exist. They are, in most cases, consistent with our theoretical frameworks. In a few important cases, they present puzzles that those frameworks do not yet cleanly resolve. And they represent the cumulative product of 14 billion years of physics operating across an extraordinary range of scales. There is a phrase used in the philosophy of science, due to the physicist Niels Bohr, to the effect that the opposite of a great truth is another great truth. The comment was made in a different context, but it applies here in the following sense. The universe, at the very largest scales, appears both to follow the rules of physics we have derived from local observations, and in some cases, to challenge those rules in ways that require either refinement or extension. Both of those things can be true simultaneously. The rules work, except when they do not. That exception is not a failure. It is the signature of a universe that is still teaching us things. At the largest scales, the universe is telling us something about its earliest moments, about the nature of the forces and particles that filled that first cosmic second, about whether the standard model of cosmology is complete or whether something is missing. The largest objects we have found are not just the biggest items in an astronomical catalog. They are probes of physics at its most fundamental level. Astronomers in the coming decade will map more of the sky to greater depth than all previous surveys combined. They will measure galaxy positions and shapes across volumes of the universe that are currently blank in our catalogs. They will trace the evolution of large-scale structure from when the universe was young to the present day with unprecedented precision. They will measure the cosmic microwave background at higher angular resolution and lower noise levels. They will detect gravitational waves from more merging black holes and neutron star pairs. Each of these datasets will be tested against the predictions of the standard model. Where the model succeeds, confidence in it will increase. Where it fails, the deviations will constrain what the replacement or extension needs to look like. The Hercules Corona Borealis Great Wall will either survive this scrutiny as a genuine anomaly requiring new physics, or dissolve into a statistical artifact that the standard model accommodates. Either outcome is scientifically valuable. What drives this work is not the record-keeping impulse, the desire to have the biggest number or the most impressive object. It is the deeper question underneath all of it. Why does the universe look the way it does? Why these structures, at these scales, with these distributions? Why this much dark matter and not more? Why this amount of dark energy? Why these initial fluctuations and not different ones? These are not questions with obvious answers. They are questions that the largest structures in the universe are helping to constrain, because the universe itself is the best laboratory we have. We did not build it, and we cannot run controlled experiments on it, but we can observe it from many angles and at many scales, and every observation adds a constraint. The largest objects are the end products of the full process. Understanding them means understanding the process from beginning to end. That understanding is not yet complete. The current moment in astrophysics is one of unusual richness. New instruments are coming online, new anomalies have appeared in the data, and a coherent picture of the universe exists, but has cracks in it that may signal something genuinely new. The science is not solved. The largest structures in the universe are not fully explained. The questions they raise are some of the most important in contemporary physics. That is exactly where science should be, at the edge of what is known, looking at what is not, and building the tools to find out. Something changes when you start thinking seriously about how astronomers first realized the universe was this big. It doesn't happen all at once. There is no single moment of revelation. It builds through a series of conceptual expansions, each one shocking the scientific community at the time, and each one later becoming so ordinary that students learn it without registering how much it overturned. In the early 20th century, astronomers debated whether certain fuzzy, spiral-shaped objects visible in telescopes were clouds of gas within the Milky Way or distant galaxies of their own, comparable in scale to the Milky Way itself. The answer came in the 1920s, when Edwin Hubble used a class of pulsating stars called Cepheid variables to measure the distance to the Andromeda Nebula, as it was then called. He found it was about 900,000 light-years away. Even this early estimate, now known to be too low by a factor of nearly 3, was enough to establish that Andromeda lay far outside the Milky Way. The Milky Way was not the whole universe. It was one galaxy among many. That conceptual shift is worth pausing on. Before Hubble's measurement, most astronomers believed the Milky Way was essentially the cosmos. Afterward, it became clear that the Milky Way is one of billions of similar systems. The observable universe expanded in a single measurement by a factor of roughly 1,000,000. A few years later, Hubble made a second discovery, just as transformative. By measuring the velocities of distant galaxies, he found that almost all of them were moving away from us, and that more distant galaxies were receding faster. This was the observational evidence that the universe is expanding, a relationship between distance and recession velocity now called Hubble's law. The implication, running the expansion backward in time, was that the universe had a beginning, a moment when all of space was compressed to an unimaginably small volume, what we now call the Big Bang. These discoveries, within a decade of each other, transformed cosmology from a philosophical, speculative discipline into a quantitative science with measurable starting conditions. Every subsequent discovery built on this foundation. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories provided direct confirmation of the hot early universe implied by the Big Bang model. The background radiation they detected matched theoretical predictions almost exactly. It remains today one of the most precisely verified predictions in the history of physics. The recognition in the 1980s and 90s that dark matter was not just a convenient assumption, but a necessary component of any model of galaxy formation and large-scale structure, came from the convergence of multiple, independent lines of evidence. Galaxy rotation curves, which showed stars in the outer regions of galaxies orbiting too fast to be explained by visible matter alone, were one such line. Gravitational lensing, in which the light from background galaxies is bent and distorted by the matter in foreground clusters, provided another. The cosmic microwave background anisotropies provided a third. Each independent measurement pointed to the same conclusion. There is far more matter in the universe than what we can see. And then came dark energy. In 1998, two independent teams of astronomers studying supernovae at cosmological distances arrived at the same unexpected result. The universe's expansion is not slowing down under the influence of gravity, as expected. It is speeding up. Something is pushing space apart, and the push is getting stronger over time as the universe grows. That something, which we call dark energy, and about which we understand essentially nothing beyond its existence and its magnitude, turned out to be the dominant component of the universe's energy budget. Each of these discoveries was a shock. Each one required the scientific community to revise a fundamental assumption, and each one added a layer of complexity to the universe we thought we understood. That historical pattern matters because it should inform our expectations about the current anomalies, including the Hubble tension and the apparent scale of the Hercules Corona Borealis Great Wall. The history of cosmology strongly suggests that when precise measurements disagree with prevailing models, the models need revision. The revisions have sometimes been modest, a parameter adjustment, or a new component. Sometimes they have been fundamental, like the introduction of dark energy or the acceptance of a Big Bang origin. We do not know in advance which kind of revision the current anomalies require. That is precisely why they are interesting, and precisely why the next decade of observations, with the instruments currently being built and the methods currently being refined, is being anticipated with such attention by the scientific community. There is a particular kind of scientific patience required in this field. The timescales involved in obtaining the key measurements are long. Building a next-generation telescope takes a decade. Accumulating the data needed to answer a specific cosmological question can take years of observation time. Processing and analyzing that data takes additional time. Peer review adds more. By the time a result is published and assessed, it is not unusual for 15 or 20 years to have passed since the original question was posed. This is very different from, say, particle physics, where a key experiment can be designed, built, and completed in a few years with a focused team. Cosmology operates on the timescale of the phenomena it studies, which are themselves measured in billions of years. The science moves at the speed that nature allows. What this means in practice is that the questions open today about the Hercules Corona Borealis Great Wall, about the Hubble tension, about the formation of the most massive black holes, will likely still be in some sense open 5 years from now, and significantly clearer 10 years from now, and probably resolved one way or another in the context of 21st century scientific progress, which is what passed for a very long time by human standards, but a very short time by cosmological standards. In the meantime, the structures themselves sit there in the universe, indifferent to our questions about them. Stephenson 218 continues to cool at an imperceptible rate. Phoenix A star continues to slowly accumulate matter from the surrounding cluster gas, though at a diminished rate compared to its quasar-era peak. The filaments of the cosmic web continue to drain matter from voids into clusters. The Hercules Corona Borealis Great Wall, if it is real in the way its discoverers claim, continues to exist across 10 billion light-years of space, in a configuration that raises questions our current theory cannot cleanly answer. The universe does not wait for us to understand it. It just is, at every scale simultaneously, from the smallest quantum fluctuation to the largest structure we can detect. We build the tools to see it as clearly as we can, and then we look. What we have seen already is extraordinary. What we expect to see in the coming decades, with better instruments and better methods, is likely to be more extraordinary still. The history of the field offers no reason to expect that the universe will become less surprising as our knowledge improves. Every time we have resolved an existing mystery, new ones have appeared behind it. The largest objects in the universe are, in the most literal sense, the largest open questions in science. At the outer boundary of all this, there is something that rarely gets acknowledged in discussions of cosmic scale. The observable universe is not the whole universe. It is the portion of the universe from which light has had time to reach us since the Big Bang. Beyond the observational horizon, space continues. The question is, how much? In the simplest standard models, the universe is spatially infinite. If space is flat, as current measurements suggest to high precision, it extends without boundary, in all directions. An infinite universe would contain infinite matter, organized in patterns that reflect the same physics as what we observe, but with variations. Distant regions where the density fluctuations happen to produce different arrangements, different galaxy distributions, possibly even different histories of structure formation. In some theoretical frameworks, including inflation, which is the leading model for the rapid expansion of the very early universe, the universe may be far larger than the observable volume. with different regions potentially having different physical properties, depending on how inflation played out locally. In the most extreme versions of this, sometimes called eternal inflation, there are essentially infinitely many regions, each with potentially different physics. None of this can be tested directly with current or foreseeable instruments. The observable horizon is a hard boundary imposed by the finite speed of light and the finite age of the universe. No instrument we can build will ever show us what lies beyond it in real time. What we can do is constrain the global properties of the universe using the patterns in the cosmic microwave background, which carry information about very large scales, including potentially scales larger than the observable universe. Those constraints currently suggest that if the universe is finite, it is very large. Current measurements place the minimum size of the universe at many times larger than the observable volume. If the universe is finite and curved, the curvature is so small that the edges are far beyond our horizon. For the purposes of the size hierarchy we have traced, from rocky planets to great walls, this reminder that the observable universe may be a tiny fraction of the full universe adds a further layer to an already vertiginous picture. The Hercules Corona Borealis Great Wall, spanning perhaps 10 billion light-years, is a substantial fraction of the observable universe's radius of 46 billion light-years. It is an enormous structure by any measure, and yet it may be a minor local fluctuation in a universe that extends for distances we cannot conceive of, containing structures we will never be able to observe. That possibility is not provable and not disprovable with current science. But it is an honest acknowledgement of where the limits of knowledge lie, and what lies beyond those limits, in principle, if not in practice. What we can observe, we observe as carefully as we can. The structures we have traced in this survey represent the best current answer to the question of what the largest objects in the universe are. That answer is a work in progress, as all scientific answers are. But it is the most precise work in progress humanity has ever produced on this question. From a rocky planet 12,000 kilometers wide to a wall 10 billion light-years long, the universe has filled the available scales with structures that reflect, at every level, the physics of their formation and the history of the cosmos. Understanding them is understanding where we came from, what we are part of, and how extraordinary it is to exist in a universe this complex, this vast, and this knowable. There is a measurement technique astronomers use that sounds almost too simple to work at cosmological distances, and yet it has proven to be one of the most powerful tools for understanding the scale of the universe. It is called standard candles, and the concept goes like this. If you know how intrinsically bright something is, and you can measure how bright it appears in your telescope, the difference between those two numbers tells you how far away it is. Light follows an inverse square law. Double the distance, and an object appears 4 times dimmer. This is predictable, reliable physics. The challenge is finding objects whose true brightness you know in advance. Cepheid variable stars were the first effective standard candle. These are pulsating stars whose brightness oscillates in a period that is directly related to their intrinsic luminosity. Brighter Cepheids pulsate more slowly. Once you know the period, you know the luminosity. Then you observe the apparent brightness and calculate the distance. Hubble used this technique to establish the distance to Andromeda, launching the era of extragalactic astronomy. Type 1 A supernovae extended this approach to much greater distances. These are the thermonuclear explosions of white dwarf stars that have accumulated enough mass from a companion to trigger runaway nuclear fusion. Because the explosion is triggered at a consistent mass threshold, the peak brightness is nearly identical for all Type 1a supernovae. By measuring their apparent brightness across billions of light-years, astronomers establish the distance scale well into the regime where the universe's expansion and acceleration become measurable. The discovery of dark energy came directly from this technique. When the 2 supernova teams in 1998 found their distant supernovae to be fainter than expected, they were finding that those supernovae were farther away than the expansion rate of the universe should have placed them. The universe had expanded faster than they predicted since those supernovae exploded. That meant the expansion was accelerating. And that meant something was driving the acceleration. Dark energy. What is worth emphasizing is how indirect this entire chain is. Astronomers did not observe dark energy. They observed light from exploding stars. They applied a relationship between intrinsic and apparent brightness derived from nearby stars. They fit those distances to a model of the universe's expansion history. They found the model required a new component to fit the data. They called that component dark energy. The conclusion is solid, reinforced by many independent measurements since then. But the chain from observation to conclusion is long, and each link was independently verified before the community accepted the result. This is the standard practice in observational cosmology. The universe's largest and most extreme objects are never directly accessible. What is accessible is light, and occasionally other forms of radiation, such as gravitational waves, that those objects emit or scatter. The inferences drawn from that light depend on physical models that must themselves be validated. The validation comes from applying those models to situations where the answer is already known through some other means, and confirming that the model gives the right answer before trusting it at greater distances or more extreme conditions. Every step outward in distance is a step deeper into inference. Measuring the distance to a nearby star can be done with triangulation using Earth's orbit as a baseline, a technique called parallax that requires no assumptions about the physical nature of stars. Measuring the distance to nearby galaxies requires Cepheid variables, which requires understanding the period luminosity relationship, which was calibrated using parallax distances. Measuring distances across billions of light years requires type 1a supernovae, which requires understanding their intrinsic brightness, which was calibrated using Cepheid-based distances to nearby supernovae. The ladder of inference has many rungs, and an error at any rung propagates to all the ones above it. The Hubble tension may reflect an error of exactly this type. One possible explanation is that the local distance ladder, which uses Cepheids and supernovae to measure the current expansion rate, contains a systematic error that causes it to overestimate distances, and therefore the expansion rate. Finding that error, if it exists, would require identifying where in the ladder the calibration goes wrong. Teams working on this have checked and rechecked every rung without finding a clear culprit, which is why the tension persists, and why the alternative explanations involving new physics remain on the table. The stakes of getting this right are not abstract. The expansion rate of the universe determines the age of the universe. It determines how much time has passed since the Big Bang. It determines how long large-scale structures have had to assemble. A discrepancy of 8% in the Hubble constant translates to a corresponding uncertainty in the universe's age and in all the timescale estimates that depend on it. For the question of how the largest structures formed, timescale matters enormously. The difference between a universe that is 13.6 billion years old and one that is 14.5 billion years old is almost a billion years of additional growth time for structures like galaxy, clusters, and filaments. Understanding the universe's scale is therefore not just a matter of measuring the biggest objects and writing the numbers down. It is a deeply interconnected problem in which every measurement depends on every other, and where the methods used to measure large things must be calibrated against small things, and where the small-scale physics we understand most precisely feeds into models that predict the behavior of the largest structures we observe. That interconnection is part of what makes cosmology unusual as a scientific discipline. In chemistry, you can study a molecule in isolation from the rest of the universe. In ecology, you can study a habitat without knowing the internal structure of every atom in every organism. In cosmology, the local and the cosmic are inseparably linked. The properties of the electron determine how neutral hydrogen formed, which determines when the cosmic microwave background was released, which determines the pattern of initial fluctuations, which determines the distribution of galaxies today, which determines the sizes of the largest structures. A scientist studying the spectrum of hydrogen in a laboratory is, in a very real sense, studying the same physics that produced the Hercules Corona Borealis Great Wall. The same equations, applied at different scales and different conditions, connect the smallest accessible measurements to the largest observable structures. This unity of physics across scales is one of the most profound things we have learned about the universe. It was not obviously true in advance. It is something that had to be discovered, piece by piece, over the course of centuries of observation and theory, and it remains incomplete. The dark matter and dark energy that dominate the universe are not part of the standard model of particle physics, the framework that describes all the ordinary matter and forces we can test in laboratories. There is an enormous gap between what particle physics knows and what cosmology needs. Bridging that gap is one of the central challenges of 21st century physics, and the largest structures in the universe are some of the most stringent tests of any proposed bridge. If a new particle explains dark matter, its properties must be consistent with the observed clustering of dark matter on small scales, on galaxy scales, on cluster scales, and on the scale of the cosmic web. If a new field explains dark energy, Its behavior must be consistent with the observed expansion history from the Big Bang to today, including whatever role it plays in the Hubble tension. If there is new physics that explains the Hercules Corona Borealis Great Wall, that physics must also be consistent with everything we know works in the standard model of cosmology. This is why anomalies at the largest scales are taken seriously, even when the evidence for them is uncertain. They are windows into physics that the small-scale, high-energy experiments at particle colliders cannot access. The universe, at its largest scales, is an experiment we did not design and cannot control, but it is running under physical laws we can, in principle, understand, and the structures it has produced are data that constrain those laws. The largest objects in the universe, from the biggest stars to the widest cosmic walls, are therefore not endpoints of a catalog. They are questions in physical form. Answering them requires the full range of scientific tools: telescope observations, theoretical models, laboratory measurements of particle properties, gravitational wave detectors, and the patient accumulation of data across decades and generations. That is what science looks like when it is working on the hardest problems available. Not a single dramatic moment of discovery, but a sustained and collective effort, building instruments, developing methods, gathering data, and slowly narrowing the range of possible answers until the right one becomes clear. The universe has been doing this without us for 13.8 billion years. We have been paying attention for a few hundred years, and carefully for perhaps a century. In that time, we have gone from not knowing whether our galaxy was the whole of the cosmos to measuring cosmic walls spanning a tenth of the observable universe. The progress is remarkable by any standard. What remains unknown is larger than what is known. That is both the challenge and the invitation. Every time an astronomer points a telescope at the sky and records what it sees, they are adding a data point to the largest scientific project in human history. The effort to understand why the universe is organized the way it is. At every scale, from the smallest to the most incomprehensibly vast, the largest objects we have found are the most dramatic results of that effort. They represent the full reach of what 14 billion years of physics can build. And they are telling us, in their sizes and distributions and anomalies, that we do not yet have the full story. The full story, when we get closer to it, will be more intricate and more surprising than anything we currently imagine. The history of cosmology gives us every reason to believe that. There's a particular kind of vertigo that comes from thinking carefully about what light years mean in practice, not just as a unit, but as a physical fact. When you look up at Betelgeuse, the light entering your eye left that star somewhere between 500 and 700 years ago, depending on which distance estimate you use. The exact moment it departed Betelgeuse is uncertain because the distance itself is uncertain, but we know it took centuries to arrive. Medieval astronomers looking at the same star were seeing light that had already been traveling for hundreds of years before they were born. When we observe a galaxy a billion light years away, we are seeing it as it was a billion years ago, when multicellular life on Earth was only just beginning to diversify in the oceans. When we observe the most distant known galaxies, over 13 billion light years away, we are looking at objects that formed when the universe was less than a billion years old, when stars first began to ignite and the first heavy elements were being forged. The cosmic microwave background, the afterglow of the hot early universe, is light that has been traveling for approximately 13.8 billion years and shows us the universe as it was when it was roughly 380,000 years old. At that point, the universe was a smooth, nearly featureless sea of gas. Looking at the microwave background is looking at the raw material from which everything we have discussed, every planet, star, black hole, galaxy, and cosmic wall, eventually assembled. This temporal aspect of observation adds a dimension to scale that the simple size comparisons cannot capture. We do not observe a static universe. We observe a temporal cross-section with nearby objects showing us the current era and distant objects showing us progressively earlier eras. Assembling a coherent picture of the universe from this cross-section requires understanding how the universe has evolved, which is itself a product of the same physical laws we are trying to test. The largest structures we have discussed represent the cumulative product of that evolution at different stages. The galaxy clusters we observe nearby show us the current state of structure formation. The quasars we detect at billions of light years distance show us galaxies in an earlier, more active state, when their central black holes were accreting matter at much higher rates. The gamma-ray burst distributions that hint at structures like the Hercules Corona Borealis Great Wall are snapshots of where galaxies existed at specific epochs billions of years ago. Stitching these snapshots together into a continuous history requires careful theoretical modeling of how the universe evolves between the moments we can directly observe. It requires knowing not just where galaxies are, but how they got there, and whether the path they took is consistent with the physics we understand. In this sense, the largest structures in the universe are not just the biggest things we know about. They are the most complete historical records we have. They encode the full history of gravity's work on matter across the age of the universe. Reading that record correctly is one of the most ambitious goals of modern science. One of the most exciting recent developments in this effort is the direct detection of gravitational waves. Albert Einstein predicted in 1915, in his theory of general relativity, that accelerating masses would generate ripples in the fabric of space-time, analogous in some ways to how accelerating charges generate electromagnetic waves, which is another way of saying light. But the amplitude of gravitational waves produced by any laboratory-scale process is immeasurably small. Only the most extreme events in the universe generate gravitational waves strong enough to detect across astronomical distances. The first confirmed detection came in September of 2015 from the collision of two black holes, roughly 36 and 29 times the mass of the Sun, located approximately 1.3 billion light-years away. The signal lasted less than half a second and was detected by the LIGO Observatory in the United States as a change in the length of its 4-kilometer detector arms by less than 1,000th the diameter of a proton. This detection opened a completely new channel for observing the universe. Unlike light, gravitational waves pass through matter almost unimpeded. They can carry information from regions of space that are completely opaque to electromagnetic radiation, including the extremely dense environments around merging black holes and neutron stars, and in principle from the Big Bang itself. A gravitational wave background from the Big Bang, predicted by inflationary models, is one of the targets of next-generation gravitational wave observatories. If detected, it would provide a completely new probe of the universe's first moments, complementing what the cosmic microwave background tells us and probing even earlier epochs. The physics of the first fraction of a second after the Big Bang, the era of inflation and reheating, may be encoded in this gravitational wave background in a way that no other observation can access. How this connects to large-scale structure is subtle but important. The spectrum of primordial gravitational waves, if measurable, would constrain the physics of inflation, which in turn set the statistical properties of the initial density fluctuations, which in turn determined how large structures can grow. A confirmed measurement of the primordial gravitational wave background would simultaneously confirm the basic picture of inflationary cosmology and provide precision measurements of the parameters that set the initial conditions for all subsequent structure formation. This chain from the universe's first moments to today's largest structures illustrates something fundamental about how cosmology works. Every part of the story is connected to every other part. The physics of the first trillionth of a second after the Big Bang shapes the distribution of matter today. The distribution of matter today shapes the cosmic web. The cosmic web determines where the largest structures form. Knowing the largest structures precisely constrains the initial conditions. Constraining the initial conditions tests the theory of inflation. Testing inflation tells us about physics at energies far beyond what any particle accelerator can reach. This interconnected chain is not a weakness of the science. It is its greatest strength. A correct theory of the universe must be simultaneously consistent with laboratory particle physics, with stellar astrophysics, with galaxy formation, with large-scale structure, and with the cosmic microwave background. The fact that the standard cosmological model passes all of these tests simultaneously, with only a handful of tensions remaining, is an extraordinary scientific achievement. And those remaining tensions, the Hubble tension, the possible anomalies in large-scale structure, the unresolved question of dark matter's identity, are not embarrassments. They are the frontier. They are the places where the next major advances in our understanding are most likely to come from. The questions that remain open are precisely the questions that will drive the most important research of the coming decades. When future scientists look back at this era in cosmology, they will likely see it the way we see the late 19th century in physics, a period of remarkable progress, genuine puzzles, and contested interpretations that just preceded a transformation in understanding. The late 19th century had the ultraviolet catastrophe in black body radiation, the anomalous precession of Mercury's orbit, and the failure to detect the luminiferous ether. Each of these was a crack in a framework that otherwise worked remarkably well. Each of them was resolved, eventually, by revolutionary new theories, quantum mechanics and general relativity, that subsumed the old framework as a special case. No one is predicting that scale of revolution for current cosmology. The Standard Model has a much better track record than classical physics had in 1900. But no one predicted quantum mechanics or general relativity in advance either. The cracks in the prevailing picture were recognized, the need for new ideas was acknowledged, and the new ideas came from unexpected directions. What seems most likely is that the current period will be remembered as one of consolidation and refinement. The Hubble tension resolved by a modest extension of the model, the large-scale structure anomalies clarified by better surveys, the dark matter mystery solved by the detection of a new particle or field. But what is equally possible is that one of these threads leads somewhere genuinely surprising, somewhere that requires a new way of thinking about space, time, matter, or the universe's initial conditions. The largest objects in the universe are both the final products of 13.8 billion years of cosmic evolution and the data that will shape the next generation of theoretical understanding. They sit at the intersection of what we know and what we do not know, marking the outer boundary of our current comprehension and the starting point for whatever comes next. The universe has been building toward this for a long time. We have been watching, with increasingly precise instruments and increasingly refined theories, for a very short time. The watching will continue. The theories will evolve. And the universe, indifferent to our frameworks, will continue to exist at every scale simultaneously, from atoms to great walls, waiting for us to ask better questions. There is a class of object that sits in a peculiar zone between stars and planets, and it tells us something important about the continuity of physical processes across scales. Brown dwarfs are objects massive enough to briefly fuse deuterium, a heavy isotope of hydrogen, but not massive enough to sustain the proton-proton fusion that powers stars like the Sunday. They occupy the mass range from roughly 13 to approximately 80 Jupiter masses. Below 13 Jupiter masses, an object is a planet by convention. Above 80 Jupiter masses, an object ignites sustained hydrogen fusion and becomes a star. ROX's 42b, the largest known planet we discussed, sits just below that lower boundary at 9 Jupiter masses. The exact location of the boundary is not perfectly sharp. It depends on the composition of the object and on what exactly you define fusion to mean in this context. What the existence of this boundary illustrates is that the objects in the universe do not form discrete, well-separated categories. They form a continuous spectrum, with the names we apply being convenient labels for regions of that spectrum rather than fundamental divisions. The same is true of the boundary between regular black holes and ultramassive black holes. A black hole with a mass of 1 million solar masses is qualitatively similar to one with a mass of 100 billion solar masses. Both have event horizons. Both grow by accreting matter. Both distort spacetime in ways described by the same equations. The ultramassive label indicates a mass large enough that formation through ordinary stellar evolution becomes implausible and requires alternative explanations. But it is not a physically distinct category the way ice is physically distinct from liquid water. Understanding these continuities is part of understanding the size hierarchy of the universe. The objects at the extremes, the largest stars, the most massive black holes, the widest galaxy clusters, are not fundamentally different from their smaller counterparts. They are the same physics, operating at the extreme end of the distribution. What makes them interesting is both their record-setting nature and what that record tells us about the conditions that produce them. Stephenson 218 is the largest known star. Not because stars can be any size, and this one just happens to be the biggest, but because stellar physics constrains the maximum size through the Eddington limit and the dynamics of mass loss. The existence of Stephenson 218 at its recorded size, rather than growing larger, reflects a real constraint in stellar physics. Similarly, the mass of Phoenix A star reflects what is possible given the age of the universe and the maximum rate at which black holes can grow. These constraints are scientifically valuable. They are testable predictions of physical theory applied to extreme conditions. If we found a star significantly larger than what the Eddington limit permits, that would signal that something about our understanding of stellar physics is wrong. If we found a black hole with significantly more mass than current formation models allow, that would signal a gap in our understanding of black hole growth. So far, the extremes we observe are broadly consistent with theoretical expectations, which is itself a validation of those theories. The universe's largest objects exist at the boundaries of what theory allows, which is exactly where they should be if the theory is correct. The one exception, the one place where the current record holders sit in tension with theory, is the Hercules Corona Borealis Great Wall. If confirmed at its claimed dimensions, it exceeds what standard cosmological models predict for the largest coherent structure that could have assembled in the available time. That is the significance of it. Not merely that it is big, but that it is possibly too big for the framework we use to explain everything else. That tension, unresolved as it is, makes the Hercules Corona Borealis Great Wall the most scientifically interesting entry in the entire size hierarchy. Every other object on the list sits comfortably within the range of what known physics predicts. This one does not, and that makes it potentially the most important data point of all. Certainty in science is rare. Provisional confidence, based on the weight of evidence, is the actual currency of scientific conclusions. The cosmic microwave background anisotropies are known with high confidence. The existence of dark matter is known with high confidence. The accelerating expansion of the universe is known with high confidence. These are conclusions supported by multiple independent lines of evidence, tested against detailed predictions, and confirmed by independent teams using different methods. The Hercules Corona Borealis Great Wall is not in that category. It is a detection from a single method, with statistical uncertainties large enough that its existence as a coherent structure, rather than a statistical fluctuation, is not yet established beyond reasonable doubt. That does not mean it is wrong. It means the evidence is not yet at the level required for strong conclusions. Science communicates this distinction through the language of statistical significance. A result with a significance of 2 sigma, meaning 2 standard deviations from the expected value under the null hypothesis, has roughly a 5% probability of arising by chance, even if nothing real is there. 3 sigma drops that probability to about 3 in 1,000. 5 sigma, the conventional threshold for a discovery claim in particle physics, drops it to about 3 in 1,000,000. The claimed detection of the Hercules Corona Borealis Great Wall falls short of 5 sigma. How far short is itself somewhat uncertain, because the statistical analysis depends on models of the background distribution that contain their own uncertainties. This is the honest state of knowledge. Not a definitive discovery, not a definitive refutation, but an anomalous signal that warrants serious follow-up. The follow-up is ongoing. The result will be clearer in a decade. In the meantime, thinking about why it matters if it is confirmed helps clarify what is at stake. The standard model of cosmology, with cold dark matter and a cosmological constant representing dark energy, is an extraordinarily successful framework. It describes the cosmic microwave background, the large-scale structure of galaxy surveys, the abundance of light elements produced in Big Bang nucleosynthesis, and the expansion history of the universe, with impressive accuracy, using just a handful of free parameters. Any revision to this framework would need to preserve all of these successes while explaining the anomaly. That is a highly constraining requirement. It means that most proposed modifications to the standard model fail quickly because they fix one problem while breaking something that was already working. The history of cosmology is full of models that seemed promising until they were tested against the full range of observations and found wanting. The difficulty is finding a modification that fits everything simultaneously. This is also why the confirmation or refutation of the Hercules Corona Borealis Great Wall is so consequential. If it is a statistical artifact and not a real structure, the standard model continues to work without modification at the largest scales. If it is real, the standard model needs a non-trivial modification to account for it, and finding that modification will require a level of theoretical creativity comparable to what produced the current model. Either way, the science advances. Either the largest known structure is confirmed as real and forces a deeper understanding of the universe, or it dissolves into noise and the standard model's consistency is extended to an even larger scale. Both outcomes are informative. Both narrow the space of possibilities. Both bring us closer to understanding the full picture. This is ultimately what the universe's largest objects are for, scientifically speaking. Not to impress us with their size, though they do. Not to stimulate a sense of wonder, though they accomplish that too. But to serve as the most extreme tests of our understanding of physics. At the boundary of what is possible, the theory is most exposed. At the extreme, the predictive power of our models is most challenged. Every record-setting object in the universe is, in this sense, a question put to science. The largest star asks whether our models of stellar physics correctly predict the maximum size. The largest black hole asks whether our models of black hole formation correctly predict the maximum mass. The largest cosmic structure asks whether our models of cosmological evolution correctly predict the maximum scale of coherent assembly. In each case, the object has formed, exists, and sits in the universe as a fact. The question is whether the framework we have built to understand the universe is adequate to explain that fact. So far, mostly yes, with some important and active exceptions. And those exceptions are where the most important work is happening. The universe built these objects over billions of years without any regard for whether we would understand them. It built them because the physics demanded it. Our task, which we have been working on for a few centuries with serious quantitative tools, and for roughly 100 years, with instruments capable of reaching to cosmological scales, is to reconstruct the physics from the outcomes. We are doing this, imperfectly, incrementally, with occasional wrong turns and heated disagreements about interpretation. But the trajectory is clear. Every generation of instruments and theorists has understood the universe more precisely than the previous one. There is every reason to expect that trajectory to continue. The largest objects in the universe are waiting. The measurements are being made. The theories are being tested. And somewhere in the gap between what we know and what we do not yet know, the next major advance in our understanding of the cosmos is waiting to be found. There is a conversation happening right now in physics departments and observatory control rooms that does not make it into most popular accounts of cosmology, because it is not about a single dramatic discovery. It is about a slow accumulation of tension, measurements that almost agree but do not quite, predictions that hold in almost every regime but slip in a few, datasets that are internally consistent but inconsistent with each other. The measurements are getting better. The disagreements are getting louder, not quieter. And within those disagreements, at the edges where the numbers refuse to line up, is where the genuinely new physics may be hiding. Consider what we have learned about the formation of the most massive black holes. The standard picture of black hole growth through stellar evolution and accretion works well for objects up to a few billion solar masses. Black holes of that mass exist in sufficient numbers in old enough galaxies, with enough time in the universe's history that their formation can be explained within the standard framework. But as we push to higher masses, as we catalog objects like Phoenix A star with its 100 billion solar masses, the explanations become strained. The problem is time. A black hole growing by swallowing one solar mass per year, which is already an aggressive rate, would take 100 billion years to reach Phoenix A star's mass. The universe is only 13.8 billion years old. Even allowing for periods of faster accretion, even allowing for mergers between large black holes, the arithmetic is challenging. Not impossible, challenging. The question of whether the standard picture of black hole growth is sufficient at the highest masses, or whether some alternative formation channel like primordial black holes is required, is unresolved. The data we have on the most massive black holes comes primarily from X-ray observations of galaxy clusters and from the spectral properties of quasars. Neither source provides certainty. X-ray observations of clusters depend on models of the hot gas dynamics. Quasar spectra give mass estimates through reverberation mapping, a technique that has been validated for lower mass systems but is extrapolated to the highest masses without direct confirmation. Future X-ray observatories, particularly the Lynx mission concept and the Athena mission planned by the European Space Agency, will measure the properties of the hot gas in galaxy clusters with dramatically improved precision. They will detect fainter X-ray sources at greater distances, extending the inventory of massive black holes to earlier cosmic epochs. That extended inventory will test whether the population of massive black holes we observe today is consistent with standard growth models applied over the full age of the universe. If the models work, that is a successful prediction confirmed. If they fail, that is a signal pointing toward new physics, potentially primordial black holes, potentially new accretion physics, potentially something else entirely. The observation will not leave the question open indefinitely. It will close it, one way or another. The same logic applies to the Hercules Corona Borealis Great Wall. The observation exists. The statistical uncertainty is real, but finite. Better data will reduce that uncertainty. When the reduction is sufficient, the question of whether this structure is real, and of the claimed size, we'll have a definitive answer. The path to that answer runs through galaxy surveys that are currently being planned and in some cases already being conducted. What makes the current moment in observational cosmology distinctive is that multiple questions are approaching resolution simultaneously, with instruments of unprecedented capability coming online or nearing completion. The James Webb Space Telescope, launched in December of 2021, is already transforming our understanding of the early universe by detecting galaxies that formed within the first few 100 million years after the Big Bang. Some of those early galaxies appear to be more massive and more evolved than expected at such early times, hinting again at possible gaps in the standard model of galaxy formation. The Vera C. Rubin Observatory will conduct the Legacy Survey of Space and Time, photographing the entire visible southern sky every few nights for 10 years, building an extraordinary catalog of transient events, including supernovae useful for Hubble constant measurements, and static objects, including billions of galaxies useful for large-scale structure analysis. This single survey will produce more observational data than all previous ground-based surveys combined. The Square Kilometer Array will detect radio emission from neutral hydrogen in galaxies across cosmic history, tracing the evolution of gas, the raw material of stars, from shortly after the Big Bang to today. This will provide a completely new lens on how structure has grown, complementing the optical and infrared galaxy surveys that dominate current large-scale structure studies. The Nancy Grace Roman Space Telescope will conduct an infrared sky survey covering more area than the Hubble Space Telescope has imaged in its entire history, with similar depth and sharpness in a small fraction of the time. It will detect hundreds of millions of galaxies, measuring their shapes with precision sufficient for detailed gravitational lensing analyses that will independently constrain the distribution of dark matter and the growth of large-scale structure. Together, these instruments will produce a comprehensive observational dataset that will test our current models more stringently than anything done before. The tensions that currently exist will either grow or dissolve in this new data. Some open questions will be closed. New questions, almost certainly, will be opened. That cycle, question, instrument, data, analysis, new question, is the rhythm of science at the frontier. It does not end. There is no final answer, at which point the universe's secrets are exhausted, and the telescopes can be retired. The universe is not that obliging. Every instrument reveals what previous instruments could not see, and what it reveals invariably includes surprises. The surprises are what make the work meaningful, not because scientists enjoy confusion, but because each surprise is information. Each observation that does not match the prediction is a clue. Each clue constrains the theory. Each constraint on the theory narrows the space of possible universes, and narrowing the space of possible universes is what understanding the actual universe means. The largest objects in the universe, from Stephenson 218's 3 billion kilometer width to the Hercules Corona Borealis Great Wall's 10 billion light-year span, are at the outer edge of that narrowing. They represent the most extreme cases that current observations have found. They are not the edge of what exists. They are the edge of what we can currently see. Beyond them, in the unobserved volume of the universe, and in the eras of cosmic history not yet fully mapped, there may be structures and objects that will add new entries to the record books and new questions to the agenda. We will find them. Not because finding record-setting objects is itself the goal, but because the instruments we are building to understand the universe's physics will see them in the process. They will appear in the data alongside everything else, and they will need to be explained, and the attempt to explain them will advance the science. That is the situation. A universe of extraordinary size and complexity, instruments of unprecedented capability to observe it, theories that work remarkably well but have visible cracks, and a community of scientists actively working on all of it simultaneously. The largest objects we have discussed are part of this ongoing story. They are not its conclusion. They are among the most important current chapters. And the chapters ahead, written by observations not yet made and theories not yet formulated, will almost certainly be more remarkable still. The universe built itself across 14 billion years. We are only beginning to read what it built. There is an old thought experiment in physics that goes like this. If you could somehow freeze the universe in place at this exact moment and examine it, what would you find at the very largest scale? Not galaxies, not clusters, not superclusters. The very largest organizational principle of matter in the universe. What is the ultimate structure? The answer, as best as we currently know, is a network. Cosmologists call it the cosmic web, and the name is apt in the most literal sense. Imagine a three-dimensional spider web stretched across the entire observable universe. Its strands made not of silk, but of dark matter and galaxy-studded gas filaments. Its nodes where the strands intersect, packed with the densest clusters of galaxies, and the spaces between the strands almost completely empty. That is what the universe looks like at the largest scales that have been carefully mapped. The voids between filaments are not nothing. They are almost nothing. Regions where dark matter and ordinary matter are both well below the cosmic average density, where galaxies are rare and isolated, where the large-scale gravitational field is weak and dominated by the pull from surrounding overdense regions. The largest known void, sometimes called the Boots void, spans roughly 330 million light-years and contains far fewer galaxies than the average region of similar size. But even the Boots void has some galaxies in it. The cosmic web does not have true voids in the mathematical sense of empty sets. It has regions of extremely low density separated by regions of high density, with a continuous gradation between them. The filaments themselves are not like fiber cables laid along straight lines. They are irregular, branching, sometimes bent or kinked. They connect clusters to other clusters via bridges of gas and dark matter that can stretch hundreds of millions of light-years. Where multiple filaments intersect, galaxy clusters sit as the densest nodes of the network. The Milky Way's own local group sits in a relatively sparse region, not in a major cluster node, but in a filament connecting larger structures at greater distance. Mapping this web precisely requires measuring the positions of hundreds of millions of galaxies across a significant fraction of the observable universe. The Sloan Digital Sky Survey accomplished this to a depth of a few billion light-years across a substantial slice of the sky, revealing the web's texture in remarkable detail. What emerged from that mapping was not just a visual impression of a cosmic web, but a precise statistical characterization. The two-point correlation function of galaxies, which measures the excess probability of finding pairs of galaxies at given separations, matched theoretical predictions from the standard model with impressive accuracy across a wide range of scales. That match is one of the strongest current validations of the cold dark matter model of structure formation. The web we observe is, in its statistical properties, the web that cold dark matter predicts. Not in every detail, not at every scale. There are tensions, but in the broad features that characterize the overall pattern, the match is good. What new surveys will probe is the smaller deviations from this pattern, the places where the observed web differs from the predicted web by amounts that current surveys cannot yet measure. Some of those deviations may reflect physics beyond the cold dark matter model. A non-standard dark matter particle with different velocity properties, or a modified theory of gravity, or a different history of dark energy. Others may simply reflect the inherent randomness of the initial conditions, which can produce rare regions that differ significantly from the statistical average. Distinguishing between these possibilities requires precision measurements across large volumes. It requires surveys that are not just deep, reaching far into the universe, but wide, covering enough area that the statistics are robust. The combination of depth and width needed to test the largest structures is exactly what the next generation of surveys is being designed to achieve. In parallel with these observational advances, theorists have been developing increasingly sophisticated computer simulations of cosmic structure formation. These simulations model the gravitational collapse of dark matter, the hydrodynamics of gas, the formation and evolution of stars, and the feedback effects of black holes and supernovae on surrounding gas. The most advanced current simulations, like Illustris TNG and Eagle, run on some of the largest supercomputers available and track billions of simulated particles across cosmological volumes. These simulations produce synthetic universes that can be compared directly to observations. A simulated galaxy survey can be produced from the simulation and compared to an observed galaxy survey using the same statistical tools. Where they agree, the model is validated. Where they differ, the model needs refinement. The refinement might involve adjusting the numerical recipes for star formation and feedback, or it might involve changing the underlying cosmological model, including the properties of dark matter and dark energy. Current simulations can reproduce the broad features of the cosmic web, the existence of clusters, filaments, and voids, with good fidelity. They struggle with some details of individual galaxies, particularly the distribution of galaxy morphologies and the star formation rates at different epochs. But at the scales of superstructure formation, the large scales relevant to Quipu and potentially to the Hercules Corona Borealis Great Wall, simulations generally agree with the standard model predictions. The Hercules Corona Borealis Great Wall, if real, would be a structure at a scale that current simulations do not reproduce. No known simulation of the Standard Model produces a coherent structure of that length within the age of the universe. That is the specific theoretical problem it poses. Future simulations, running on the next generation of supercomputers with petaflop and eventually exaflop capabilities, will model larger volumes with higher resolution, allowing more direct tests of whether extreme structures, like the Hercules Corona Borealis Great Wall, can emerge as statistical fluctuations of the Standard Model or require something beyond it. These computational tests are as important as the observational tests. A structure that appears anomalous, based on current theoretical estimates, might be shown to be a natural fluctuation when simulated with sufficient statistical coverage. Conversely, a structure that seems within the range of Standard Model fluctuations, when analyzed statistically, might be shown by simulations to require an unrealistic combination of conditions that effectively never occurs in Standard Model. Universes. The interplay between observation, simulation, and theory is what drives cosmology forward. No single tool is sufficient. Observations provide the data that theory must explain. Theory provides the framework that simulation implements. Simulation provides predictions that observations can test. The cycle runs continuously, with each rotation producing a more refined picture of how the universe works. At the end of that process, what we get is understanding. Not certainty, which science can rarely provide, but understanding, a framework that correctly predicts what we observe across the widest possible range of conditions, with the smallest possible set of assumptions, and with known limitations that tell us where to look for what is missing. The largest objects in the universe are both the subject of this understanding and among its most demanding tests. From the rocky planet, 4 times Earth's diameter, to the 10 billion light-year wall, the inventory of cosmic structures challenges our theories at every scale and rewards the theories that succeed. The record setters, the monsters, the anomalies, are not distractions from the main story of how the universe works. They are among its most important chapters. We are still in the middle of reading those chapters. The pages ahead are being written right now, in the data streams of operating telescopes, and the outputs of running simulations and the notebooks of theorists working late into the night. When those pages are read, the picture of the universe's largest structures will be more complete, more precise, and likely more surprising than it is today. It always has been. It will be again. There is something disorienting about the way the universe gets bigger the harder you look. This is not a poetic observation. It is a historical pattern with a reliable track record. Every time astronomers have built instruments powerful enough to see farther than before, what they have found has turned out to be larger, more structured, and more surprising than the prevailing model predicted. In the 1920s, the universe was thought to be a few tens of thousands of light years across. After Hubble's measurements of Cepheids in Andromeda, it was clear the universe contained at least millions of light years of space. By the mid-20th century, surveys of galaxy clusters revealed a universe structured on scales of hundreds of millions of light years. By the late 20th century, maps of the cosmic web had pushed the scale of coherent, large-scale structure past the billion light-year mark. Each expansion of scale was not simply a refinement of what was already known. Each was a conceptual overhaul. The universe of the 1920s and the universe of the 1990s are not the same universe with better numbers attached. They are different conceptual objects that happen to share some features. The discovery of dark energy in 1998 was not a small numerical correction to the prevailing picture. It revealed that the dominant component of the universe's energy budget was something no one had correctly anticipated. This history does not guarantee that the next major observation will produce another revolution, but it does mean that treating the current picture as the final picture would be a historically anomalous confidence. Every generation of scientists has made that mistake to some degree, and every generation has been surprised. The structures at the top of the current catalog, the Hercules Corona Borealis Great Wall, the ultramassive black holes, the red hypergiants at the edge of what stellar physics permits, sit at the boundary of our current measurement capability. The boundary is moving, as it always has. What lies just beyond it is not knowable in advance, but the evidence of history is that something interesting is there. That is not mysticism. That is the track record of a universe that has consistently demonstrated more variety and more extremity than any model developed before the measurement. The model is always built from the data available at the time. The data available at any time is always smaller than the universe, And the universe, indifferent to our models, continues to contain objects and structures at scales we have not yet reached. We have reached, so far, a remarkably long way. From a planet 12,000 kilometers wide to a wall 10 billion light-years long, across 15 orders of magnitude of physical size, from one extreme to the other. The physics connecting those extremes, quantum fluctuations to cosmic filaments, is increasingly well understood, with important exceptions. The exceptions are where the next understanding is hiding. Finding that understanding is the work of the coming decades. The instruments are nearly ready. The questions are clearly posed. The universe is waiting to be asked them. Before leaving this subject entirely, it is worth saying something about what the act of measurement itself means for the objects we have discussed. Stephenson 218 does not know it is the largest known star. Phoenix A star does not know it holds the record for the widest event horizon. The Hercules Corona Borealis Great Wall, if it exists as a coherent structure, has no awareness of the theoretical tension its existence creates. These objects exist, independent of our measurements. They existed before we knew about them. They will exist after we have refined our estimates of their dimensions. What changes with measurement is our knowledge, not the objects. And what our knowledge of these objects does, once we have it, is constrain reality. Every confirmed measurement of a record-setting object is a demonstration that the universe is capable of producing that object, that the physics of stellar structure, or black hole growth, or large-scale matter distribution permits objects of that size and mass to exist. Every constraint is a step toward understanding the boundary conditions that physics places on cosmic structure. We are the only part of the universe, as far as we know, that looks back at the rest of it and tries to understand it. The cosmic web does not study itself. The supergiants do not calculate their own Eddington limits. The black holes do not measure their own event horizons. We do these things, from this small planet, using instruments we have built and theories we have derived, across distances that make the distance from Earth to the Moon look like the width of a doorway. That this is possible at all is itself a remarkable fact. That it continues to work, that the physics derived in laboratories applies to objects billions of light years away and billions of years in the past, is evidence of something deep. The universe operates according to consistent laws everywhere and always, and those laws are, with sufficient care and creativity, intelligible to the minds that have evolved within it. The largest objects in the universe are the most distant expressions of those laws we have yet found. They are distant in space, in time, and in the extremity of the conditions that produce them, and yet they are not beyond understanding. They are, with effort, reachable, if not physically, then intellectually, through the chain of inference that runs from telescope to mind. That chain is what science is. It is the most powerful tool humans have ever developed for understanding reality. It is imperfect, self-correcting, and cumulative. It has already carried us from a planet 12 centimeters across to a wall spanning a tenth of the observable universe. Where it will carry us next, no one can say with certainty. But if history is any guide, it'll be further than we currently expect. And what it will find there will be, in the best tradition of scientific discovery, both stranger and more coherent than anything we currently imagine.